So here's something worth thinking about as you settle in tonight. Right now, as you hear my voice, something extraordinary is happening inside your head, and it's happening so fast and so seamlessly that you've never once in your life had to think about it. My vocal cords are vibrating, roughly 150 times every second, pushing tiny parcels of air back and forth in a pattern that encodes everything I'm saying, every word, every pause, every rise and fall of inflection. Those parcels of compressed air are radiating outward, spreading through a room somewhere, hitting a microphone diaphragm thinner than a sheet of paper. That diaphragm is converting the mechanical pressure into an electrical signal.
That signal is being amplified, processed, compressed into a stream of numbers, sent across a network, decoded by your device, fed through a tiny digital to analog converter, pushed out through a speaker or a pair of earbuds, and turned back into pressure waves in the air around your ear. Those pressure waves enter your ear canal, strike a membrane about the size and thickness of a small fingernail, set 3 of the tiniest bones in your body into motion, transfer that motion into a fluid-filled spiral the size of a pea, bend microscopic hair cells thinner than a strand of spider silk, and trigger electrical impulses that race along your auditory nerve at roughly 100 meters per second into your brain. And your brain, without any conscious effort on your part, reassembles all of it into language, into meaning, into the feeling of someone talking to you quietly in the dark.
That entire chain, from vibrating vocal cords to conscious understanding, involves at least a dozen transformations of energy, mechanical to acoustic to electrical to digital to electrical to acoustic to mechanical to hydraulic to electrochemical to neural. At every single link, the energy changes form completely, and at no single link is any of the meaning lost. The information that started as a thought in my mind arrives as a thought in yours, passing through air and wire and silicon and bone and fluid and nerve along the way, and the whole journey takes less than a second. Think about what that means for a moment. Every conversation you've ever had, every song you've ever loved, every time someone called your name from across a room and you turned your head, that chain was firing. Every link had to work. Every transformation had to preserve the pattern.
And each one of those links, each step in that chain, represents a chapter in one of the longest and most fascinating stories in all of science. The story of how human beings figured out what sound actually is. Because here's the thing, for most of human history, nobody understood any of it. People could hear, obviously. They could make music, they could speak, they could tell the difference between thunder and a whisper. But the question of what was actually traveling through the air between a drum and an ear, between a voice and a listener, that was genuinely mysterious. The ancient Greeks had ideas. Some of them turned out to be remarkably good guesses. But it took more than 2,000 years, dozens of brilliant and sometimes obsessive people, and a series of discoveries that each unlocked the next, before we arrived at anything close to a complete picture. And the beautiful thing about this story is that it naturally follows the path of the sound itself. Each discovery answered one question about one link in the chain, and in doing so, revealed that there was another link beyond it, deeper, stranger, and more wonderful than the one before. So that's what we're going to do tonight. We're going to follow a sound on its journey, from the moment something vibrates to the moment your brain turns that vibration into meaning. And at every link in the chain, we're going to stop and ask, how does this work? And who figured it out? And what did they get wrong along the way? The journey starts with the simplest possible question, the one that the very first curious person must have asked when they plucked a string and heard a note ring out. What just happened? Why did that string make a sound? What, physically, is vibration? Let's find out. Let's go back, way back.
About 2,600 years, to a town in southern Italy. Or maybe it was the Greek island of Samos. The historical record is a little hazy on this point, but the person is clear enough. Pythagoras. You probably know him as the triangle guy, the one whose theorem you memorized in school about the squares of the sides of a right triangle. But Pythagoras was much more than a geometry teacher. He was the leader of a philosophical and mathematical community, a group that believed, with an almost religious intensity, that numbers were the fundamental fabric of reality. And the story that connects Pythagoras to the science of sound is one of those tales that has been told so many times that the legend and the facts have gotten thoroughly tangled together. But the core of it is worth telling anyway, because even if the details are embellished, the insight underneath them changed everything. The story goes that Pythagoras was walking past a blacksmith shop one day, and he heard the hammers striking the anvils. Some combinations of hammer blows sounded harmonious together, pleasant, musical. Others clashed. And Pythagoras, being the kind of person who couldn't walk past an interesting pattern without stopping to investigate, went inside and started examining the hammers. He wanted to know what physical difference between the hammers produced the difference in sound. Now, historians have picked this story apart pretty thoroughly, and the specific physics of hammers hitting anvils doesn't work out the way the legend describes. The relationship between a hammer's weight and the pitch of the sound it produces when it strikes an anvil is much more complicated than a simple ratio. But what matters, what really matters, is what Pythagoras and his followers did next with the idea that the story represents. They went home and started experimenting with strings.
And with strings, the physics actually does work out in the most elegant way imaginable. Pythagoras and his school used an instrument called a monochord, which is about as simple as a scientific instrument can be. Picture a wooden board with a single string stretched across it, fixed at both ends, with a movable bridge that you can slide along the board to change the vibrating length of the string. You pluck the string and it produces a note. Then you slide the bridge to the halfway point so that only half the string is free to vibrate, and you pluck again. The note you hear is exactly 1 octave higher than the first one. The ratio of the string lengths is 2:1. Now slide the bridge so that 2/3 of the string vibrates. Pluck it. The interval you hear between this note and the original is what musicians call a perfect fifth, the distance from the first note to the fifth note of a major scale. The ratio is 3:2.
Let 3/4 of the string vibrate and you get a perfect fourth, a ratio of 4:3. These intervals, the octave, the fifth, the fourth, were the ones that Greek musicians considered the most harmonious, the most pleasing to the ear. And they all corresponded to ratios of small whole numbers, 2:1, 3:2, 4:3. Just sit with that for a second. 2,600 years ago, with nothing more than a wooden board and a piece of string, someone discovered that the difference between a combination of notes that moves you and a combination that grates on your nerves is a matter of simple arithmetic. Beauty, the specific, undeniable beauty of musical consonants, has a mathematical structure. It can be expressed in fractions, and those fractions aren't culturally constructed or subjective or a matter of taste. They're built into the physics of vibrating objects. A string divided in half will produce an octave higher in ancient Greece, in medieval Japan, in a modern recording studio, anywhere, for anyone, always. The ratios don't change. They can't. They're a consequence of how vibration works. And this discovery did something profound. It established the idea that sound follows rules, that it isn't arbitrary or magical or the voice of the gods, that hidden beneath the apparent chaos of the audible world, there's a clean, mathematical order waiting to be found. That idea, that sound is lawful, that it can be described with numbers, is the foundation stone on which everything else we're going to talk about tonight is built. But here's what Pythagoras couldn't explain. He knew that dividing a string in certain ways produced certain intervals. He knew the ratios, but he didn't know why. He didn't know what the string was actually doing when it vibrated.
He couldn't see it. It moved too fast. And he certainly didn't understand how the vibration of a string turned into something you could hear across a room. The ratios were a description, not an explanation. They told you what happened, but not how or why. And that gap between description and explanation would persist for a very long time. For roughly 2,000 years, actually, the understanding of vibration didn't advance much beyond where Pythagoras left it. People knew that vibrating objects made sound. They knew about the ratios. Aristotle, writing in the 4th century BC, made the important observation that sound was some kind of disturbance in the air, that the vibrating object pushed the air, and that push traveled outward. He even correctly guessed that sound couldn't travel through a vacuum, because there would be nothing to push. But these were qualitative observations, philosophical musings, not precise physical descriptions.
Nobody could describe the shape of a vibration. Nobody could measure how many times a string moved back and forth in a second. Nobody could explain why a thicker string produces a lower note than a thinner one, or why a shorter string produces a higher note beyond the empirical observation that it just does. The person who finally started turning vibration from a mystery into a science was a French friar named Marin Mersenne, and he did it in the early 1600s, right at the dawn of the scientific revolution. Mersenne was one of those figures who seems to have been everywhere at once in the intellectual life of his era. He was a minim friar, a member of a religious order known for its austerity, but he was also a tireless scientist, mathematician, and, crucially, a connector of people. He corresponded with virtually every major thinker in Europe: Descartes, Galileo, Pascal, Fermat, Hobbes.
He was like the 17th century internet, shuttling ideas between people who might never have heard of each other otherwise. And among his many interests, Mersenne was fascinated by sound. In 1636, he published a massive work called Harmonie universelle, Universal Harmony, which was the most comprehensive treatment of acoustics that anyone had ever attempted. And in it, he did something that nobody before him had managed to do in any rigorous way. He worked out the mathematical laws governing how a vibrating string behaves. Mersenne's laws, as they're now called, describe the relationships between a string's frequency, the number of vibrations it makes per second, and the physical properties of the string itself. And they're beautifully intuitive once you see them. First, frequency is inversely proportional to length. The shorter the string, the higher the pitch. Cut the length in half, the frequency doubles.
That's Pythagoras' octave ratio, now expressed as a physical law.
Second, frequency is inversely proportional to the square root of the string's mass per unit length. In plain language, a heavier string vibrates more slowly, producing a lower pitch. That's why a guitar's bass strings are thicker and often wound with metal wire to add mass, while the treble strings are thin and light. Third, frequency is proportional to the square root of the tension. Pull the string tighter, it vibrates faster, the pitch goes up. Loosen it, the pitch drops. You've experienced this every time you've watched someone tune a guitar, tightening or loosening the tuning pegs to adjust each string's pitch. Think about what Mersenne accomplished. He took Pythagoras' beautiful but unexplained ratios and grounded them in physical reality. The reason a string halved in length sounds an octave higher is that it vibrates twice as fast. The reason a thicker string sounds lower is that its extra mass resists the back and forth motion. The reason a tighter string sounds higher is that the increased tension provides a stronger restoring force, pulling the string back to its resting position more aggressively, which makes the whole cycle of vibration faster. Everything connects. The ratios aren't magic, they're consequences of mass, tension, and length, three quantities you can measure with a scale, a ruler, and a weight. And this idea of the restoring force is worth pausing on, because it's the key to understanding not just vibrating strings, but vibration in general, everywhere it occurs. When you pluck a string, you pull it away from its resting position, its equilibrium. The tension in the string acts like a spring, immediately trying to pull it back. But the string doesn't just return to its starting position and stop. It has momentum. It overshoots, swinging past the center to the other side. Now the tension pulls it back again. It overshoots again, but slightly less this time because a tiny bit of energy has been lost to friction and to the air. And so the string oscillates, swinging back and forth, each swing a little smaller than the last, until eventually it settles back to rest. That cycle, that rhythmic overshooting and returning, is the heartbeat of every vibration in the universe. A tuning fork does it. A drumhead does it. The air molecules in your throat do it when you hum. A wine glass does it when you run a wet finger around its rim. Even the atoms in a solid crystal do it, vibrating in place around their fixed positions, and the collective effect of all those tiny vibrations is what we experience as temperature, what we feel as warmth. Vibration is everywhere. It's one of the most fundamental types of motion in nature,
and it always comes from the same recipe. Something displaced from equilibrium, a restoring force that tries to bring it back, and enough energy to overshoot. Give nature those three ingredients, and it will oscillate. Galileo, working about 3 decades before Mersenne, had already begun the experimental study of vibration and sound with characteristic brilliance. He was the first to clearly articulate the connection between the frequency of vibration and the pitch of sound. In his 1638 book, Discourses and Mathematical Demonstrations Relating to Two New Sciences, Galileo described scraping a chisel across a brass plate and noticing the parallel grooves it left behind. When the chisel produced a higher-pitched screech, the grooves were closer together. When the pitch was lower, they were farther apart. The spacing of the grooves, he realized, was a visual record of the frequency.
More grooves per unit length meant more vibrations per unit time, meant a higher pitch. Galileo also described an experiment that's beautiful in its simplicity. He dipped the rim of a wine glass into water and ran his finger around it to make it sing. And he noticed that the water near the rim, responding to the vibration of the glass, formed a pattern of tiny standing waves. When the pitch was higher, the wavelength of those little water waves was shorter. The glass was making the water vibrate in sympathy, and the water was making the vibration visible. It was one of the first times anyone had connected what you hear, the pitch, to what you see, the physical wavelength. The sound was still invisible, but its effects were not. Another figure worth pausing on is Ernst Chladni, a German physicist working in the late 1700s, who found a way to make vibration patterns visible in a way that is still breathtaking to watch today.
Chladni would take a thin metal plate, clamp it at the center, sprinkle fine sand across its surface, and then draw a violin bow along the edge. The plate would ring with a clear tone, and the sand would dance and bounce, migrating away from the areas that were vibrating most vigorously and settling into the lines where the plate was not moving at all, the nodal lines. The result was a pattern, often stunningly intricate and symmetrical, that revealed the hidden geometry of vibration. Different frequencies produced different patterns. A low tone might yield a simple pattern of a few lines. A higher tone would produce something more complex, with the sand forming elegant curves and intersections that looked almost like mathematical art. Chladni catalogued dozens of these patterns, now called Chladni figures, and published them in his 1802 book, Acoustics. When he demonstrated the technique for Napoleon Bonaparte, the French emperor was so impressed that he offered a cash prize to anyone who could explain the mathematics behind the patterns. That prize went unclaimed for years, until Sophie Germain, a largely self-taught French mathematician who had to submit her work under a male pseudonym because women were not admitted to the French Academy, provided a mathematical framework for understanding how thin plates vibrate. The full solution would take even longer to work out, but Chladni's sand patterns had accomplished something remarkable. They made the invisible visible. For the first time, you could see the shape of a vibration. You could see that it wasn't random or chaotic, but organized, structured, governed by rules that produced symmetry and order. And these same patterns, by the way, are directly relevant to the design of musical instruments. The body of a violin, the face of a guitar, the soundboard of a piano. These are all vibrating plates, and the way they vibrate, the specific patterns they produce at different frequencies, determines the instrument's tonal character. Instrument makers have been instinctively aware of this for centuries, tapping and flexing the wood, shaving it thinner in some places and leaving it thicker in others, adjusting the vibration patterns by hand and ear until the instrument sounds right. Chladni's figures gave a scientific vocabulary to what luthiers had been doing by feel for generations. Mersenne understood this implicitly, even if the full mathematical formalism of oscillation wouldn't be developed until later, by people like Robert Hooke with his law of springs, and eventually by Newton with his laws of motion. But Mersenne did something else that was just as important as his theoretical work on strings. He tried to measure the speed of sound, and that attempt opens up the next link in our chain, the one that takes us from the vibrating source out into the air. Because knowing that a string vibrates is only the beginning of the story. The vibration is just the first domino. For that vibration to become sound that you can hear across a room or across a valley, it has to get from the string to your ear. Something has to carry it. Something has to travel through the space between the source and the listener. And the question of what that something is, what actually moves through the air when a sound travels from here to there, turned out to be one of the most productive questions in the entire history of physics. Because the answer, once people finally worked it out, didn't just explain sound. It explained an entire category of natural phenomena that nobody had realized were all the same thing. So the string vibrates. We've established that. Pythagoras found the ratios. Mersenne found the laws. And we know that vibration comes from a restoring force pulling a displaced object back through its resting position, overshooting and repeating. But now we need to follow that vibration outward. What happens when a vibrating string pushes against the air around it? Let's picture it in slow motion. As the string swings to the right, it pushes the air molecules next to it closer together on that side. It squeezes them. That creates a tiny region of higher than normal pressure, a compression. Then the string swings back to the left, pulling away from those air molecules and leaving a small gap, a region where the molecules are slightly more spread out than usual. That's a rarefaction, a zone of lower than normal pressure. As the string continues to swing back and forth, it produces alternating bands of compression and rarefaction. High pressure, low pressure, high pressure, low pressure, rippling outward from the string in all directions. And here's the crucial detail. The air molecules themselves don't travel from the string to your ear. They jostle back and forth in place, each one bumping into its neighbor, passing the push along. If you've ever seen a stadium wave at a sporting event, the one where people stand up and sit down in sequence so that a wave appears to roll around the stadium, then you already understand this perfectly. Nobody in the crowd actually leaves their seat. Each person just stands briefly and sits back down. But the wave travels all the way around. The pattern moves. The people stay where they are. Sound works exactly the same way. The pattern of compression and rarefaction radiates outward from the source, sometimes at hundreds of meters per second, but the individual air molecules barely move at all. Each one just nudges its neighbor and returns to roughly where it started. The disturbance travels, the medium stays put. And the speed at which the pattern travels, the speed of the wave, has nothing to do with how far any individual molecule moves. It depends on how quickly the nudge passes from one molecule to the next, which in turn depends on properties of the air itself, how dense it is, and how springy it is, how readily it compresses and bounces back. This kind of wave, where the individual particles move back and forth in the same direction that the wave is traveling, has a name. It's called a longitudinal wave, and it's fundamentally different from the kind of wave you see on a rope when you flick one end. On a rope, the wave travels along the rope's length. But each point on the rope moves up and down, perpendicular to the direction of travel. That's a transverse wave. Sound in air is longitudinal. Compression, rarefaction, compression, rarefaction, pulsing outward from the source. The air molecules shuffle forward and backward along the direction the sound is heading. Now, people had a rough, intuitive sense of some of this for a very long time. Aristotle, back in the 4th century BC, proposed that sound was a disturbance in the air, that something rippled outward from a vibrating object to the listener's ear. He even made the remarkably prescient argument that sound couldn't travel through empty space, through a void, because there would be nothing to carry the disturbance. No air molecules to jostle, no medium to conduct the push. In a vacuum, Aristotle reasoned, a bell could ring all it wanted and nobody would hear it. And he was right. But saying it and proving it are very different things. And nearly 2,000 years would pass before anyone could actually test that claim. The test required a technology that simply didn't exist in Aristotle's time. The ability to create a vacuum, to pump the air out of a sealed container. And this is where the story takes us to a German city in the middle of the 17th century, and to a man who was equal parts scientist and showman. Otto von Guericke was the mayor of Magdeburg, a city in central Germany that had been devastated during the 30 Years' War. Von Guericke was deeply interested in the nature of air and vacuum, and around 1650 he invented one of the world's first effective air pumps. He's most famous for a spectacular public demonstration involving two large copper hemispheres. He placed the hemispheres together, pumped the air out from between them, and then hitched 2 teams of horses to pull them apart. The horses couldn't do it. The atmospheric pressure holding the hemispheres together was simply too strong. It was a dramatic, crowd-pleasing demonstration of the power of air pressure, and it made von Guericke famous across Europe. But von Guericke also did something quieter and, for our purposes tonight, far more important. He put a bell inside a glass jar and pumped out the air. And as the air was removed, the sound of the bell got fainter and fainter. You could still see the clapper striking the bell through the glass. The mechanism was clearly working, but with most of the air removed, the sound was nearly inaudible. Aristotle's philosophical argument, made 2 millennia earlier in ancient Greece, had just been confirmed by a physical experiment in a German workshop. A few years later, in 1660, Robert Boyle in England repeated and refined the experiment with a better vacuum pump. He placed a ticking watch inside an evacuated glass vessel. Through the glass, you could see the mechanism moving, the tiny gears turning, the hands advancing. But the ticking faded to silence as the air was drawn out. When air was let back in, the ticking returned immediately. The conclusion was inescapable. Sound needs a medium. Take away the air, and you take away the sound. The vibration is still there, the watch is still ticking, the bell is still ringing. But with nothing to carry the disturbance outward, the vibration stays trapped at the source. It has nowhere to go. Think about what that tells you. Sound is not some invisible substance that a bell emits, like perfume or smoke. It's a behavior of the medium itself. The air is the carrier. Without it, vibration is just a silent shaking. And this distinction between the source of sound and the carrier of sound is one of those ideas that seems obvious once you hear it. But it took centuries to nail down. And it's the key to understanding why sound behaves so differently in different environments. Because sound doesn't just travel through air, it travels through water, through wood, through steel, through bone, through concrete, through virtually anything that has molecules that can bump into each other. And it travels at different speeds in different materials, sometimes dramatically different speeds. In air at room temperature, sound moves at about 343 meters per second, roughly 767 miles per hour. Fast in everyday terms, but not spectacularly so. You can see its finite speed in the delay between a flash of lightning and the clap of thunder that follows.
But in water, sound travels at about 1,480 meters per second, more than 4 times faster than in air. And in steel, it's even faster, roughly 5,960 meters per second, more than 17 times the speed in air. The denser and stiffer the material, generally, the faster sound propagates through it, which might seem counterintuitive at first. Wouldn't a denser material slow things down? But density is only half the story. The other half is stiffness, how strongly the material pushes back when you compress it. Steel is much denser than air, yes, but it's also enormously stiffer. Its molecules are bound together in a rigid lattice that transmits a push almost instantaneously from one atom to the next. In air, the molecules are floating freely, bumping into each other somewhat lazily. The push takes longer to propagate. The relationship is captured in a simple formula that shows up in every acoustics textbook. The speed of sound in a material equals the square root of the material's elastic modulus, its stiffness, divided by its density. Increase the stiffness and the speed goes up. Increase the density and the speed goes down. In most solids, the stiffness factor wins by a large margin, which is why sound in steel is so much faster than sound in air, despite steel being thousands of times denser. You can experience this yourself, by the way. If you've ever pressed your ear against a railroad track and listened for an approaching train, you heard the train coming through the steel rail long before you heard it through the air. The sound traveling through the rail arrived first because the rail transmits it roughly 17 times faster. Native Americans and frontier scouts knew this trick long before anyone worked out the physics. They'd put an ear to the ground and listen for hoofbeats, picking up vibrations through solid earth that the air hadn't delivered yet.
And here's something else about different media that matters. When sound passes from one material to another, say from air into water or from water into bone, something interesting happens at the boundary. Part of the sound reflects back, and part of it passes through into the new material. The proportions depend on how different the two materials are acoustically. If they're similar, most of the sound passes through. If they're very different, most of it bounces back. This is why you can hear someone talking to you through a closed wooden door reasonably well. The wood and air aren't too different acoustically, but talking through a concrete wall is nearly impossible. The mismatch between air and concrete is so large that almost all the sound energy reflects off the surface rather than entering the wall. This also explains something about your own body that you might not have thought about. When a doctor uses an ultrasound machine to see inside you, they always apply a gel between the probe and your skin. The gel is there because the acoustic properties of the probe's surface and your skin are quite different, and without the gel, most of the ultrasound energy would reflect off your skin surface and never enter your body. The gel acts as an intermediary, bridging the acoustic gap and letting the sound waves pass smoothly into your tissues. Every time a pregnant woman sees her baby on an ultrasound screen, that image exists because someone understood the physics of how sound waves behave at boundaries between different materials. And this is where a Dutch scientist named Christiaan Huygens enters the story, and his contribution is so fundamental that it deserves some real attention. Huygens was born in 1629 into a wealthy and well-connected family. His father was a diplomat and a friend of René Descartes.
Huygens himself was one of those rare intellects who seemed to excel at everything he touched. He built some of the best telescopes of his era. He discovered Titan, the largest moon of Saturn. He invented the pendulum clock. He made foundational contributions to probability theory. And he developed a principle for understanding wave behavior that is so elegant, so far-reaching, that it's still taught in every physics course in the world today. Huygens's principle says this: imagine a wave moving through space. At any given moment, that wave has a wave front, the leading edge of the disturbance, like the crest of a wave rolling toward a beach. Now, every single point along that wavefront can be thought of as a tiny new source of its own little spherical wave. Each point sends out its own miniature ripple, expanding outward in all directions.
And the new position of the overall wavefront a moment later is just the surface that's tangent to all those tiny individual ripples. The smooth envelope that just barely touches the front of each little wavelet. If that sounds abstract, imagine standing at the edge of a still pond and tossing a whole line of pebbles simultaneously, all in a row. Each pebble creates its own circular ripple, but because they all land at the same time and in a line, the ripples overlap and reinforce each other along the front edge. What you see moving outward is a single, smooth, straight wave. Each pebble contributed individually, but the overall effect is one coherent wavefront. That's Huygens's principle in action. And the beauty of this idea is that it explains so many behaviors of waves that would otherwise seem mysterious. Take diffraction, the ability of sound to bend around obstacles. You've experienced diffraction every day of your life, even if you never knew the word for it.
You can hear someone talking around a corner, even though a wall stands between you. You can hear music drifting from behind a building on a summer evening, even though you can't see the musicians. Sound bends around edges and fills in behind obstacles. And Huygens's principle explains exactly why. When a sound wave hits the edge of a wall or a doorway, the points along the wavefront that make it past the edge each become new sources of their own little wavelets. Those wavelets radiate outward in all directions, including into the shadow zone behind the obstacle. The sound literally curves around the corner, spreading into space where you might expect silence. And the extent to which it bends depends on the wavelength. Long wavelengths, low frequencies, bend more easily around obstacles than short wavelengths. That's why bass notes travel through walls and around corners much more effectively than treble notes.
A bass guitar note, with a wavelength of several meters, bends around a doorway as easily as water flowing around a rock. A piccolo note, with a wavelength of a few centimeters, barely bends at all, casting a much sharper acoustic shadow. Huygens's principle also explains reflection and refraction. When a wavefront hits a flat surface, each point on that surface becomes a new source, and the geometry of all those secondary wavelets bouncing back gives you the law of reflection. Angle in equals angle out. When a wavefront crosses from one medium to another, say from air to water, the speed changes, and the wavelets on one side of the boundary expand at a different rate than on the other side, which bends the wavefront. One principle, three major wave phenomena, all unified. Huygens published this work in 1690, and while it was primarily about light, the framework applied to any wave, including sound.
For sound, nobody seriously doubted that it was a wave phenomenon by the late 17th century. The evidence was too direct, too visceral. You could feel vibrations. You could see their effects on surfaces, on water, on flames. The question with sound was never really whether it was a wave, but what kind of wave exactly, and how it behaved in different situations. But we're getting ahead of ourselves. We've established that sound is a longitudinal wave of compression and rarefaction that travels through a medium, and the different media carry it at different speeds. We've confirmed through the experiments of von Guericke and Boyle that without a medium, sound cannot travel at all. And we've started to see that the behavior of sound at the boundaries between materials is governed by the acoustic properties of those materials. All of this raises a very practical question, a question that people started asking seriously in the 17th century, as soon as they had the conceptual framework to pose it clearly. If sound is a wave that travels through air, how fast does it actually go? Can we measure it? Can we put a number on it? And what does that number tell us about the nature of sound itself? Answering that question turned out to be surprisingly difficult, surprisingly creative, and, in one very important case, surprisingly wrong, in a way that took 100 years and one of the greatest mathematicians in history to fix. The first person to make a serious, systematic attempt at measuring the speed of sound was, once again, Marin Mersenne. And the method he came up with in the 1630s was beautifully simple in concept, even if it was devilishly hard to execute with the tools available to him. Here's what he did. He positioned himself a known distance from a cannon. When the cannon fired, he watched for the flash, and then counted the time until he heard the boom. Knowing the distance and the time, he could calculate the speed. Simple arithmetic. Distance divided by time equals speed. The tricky part was the timing. Mersenne had no stopwatch, no precision clock, nothing that could measure fractions of a second with any reliability. He was, essentially, counting heartbeats, or tapping his foot, or using some other rough timing method, while trying to catch the exact moment the sound arrived. And the distances involved, maybe a kilometre or two, meant that the time delays were just a few seconds, with human reaction time introducing errors of 1/10 of a second or more at each end. The uncertainty was substantial. Mersenne arrived at a value of around 450 meters per second. Too high.
The actual speed of sound in air at typical outdoor temperatures is closer to 340 to 350 meters per second, depending on conditions. But for a first attempt using nothing but eyes, ears, and a rough sense of timing, it was a reasonable result. And more importantly, it established the method. Distance, time, flash, boom, calculate. Over the following decades, other scientists refined the approach. In 1709, an English clergyman and naturalist named William Derham performed what was probably the most careful measurement of the era. Derham stood in the tower of the Church of St. Lawrence in Upminster, on what was then the eastern edge of London, and watched for the flash of cannons fired from various churches and landmarks at known distances around the countryside. He averaged many observations. He accounted for wind, which can speed up or slow down the apparent speed of sound, depending on its direction. And he arrived at a value of about 348 meters per second. Think about that. A man standing in a church tower in 1709, watching distant flashes, clicking a pocket watch, and he nailed the speed of sound to within about 1.5% of the modern accepted value. The instruments were crude, the technique was simple, but the care, the patience, the sheer number of observations he averaged over, those produced a result of startling accuracy. Sometimes good science doesn't need fancy equipment. It just needs someone who's willing to stand in a cold church tower and watch cannons fire all day. Now, measuring the speed of sound experimentally is one thing. Understanding why the speed is what it is, deriving it from first principles, from the fundamental properties of air, that's a different challenge entirely.
And this is where one of the greatest scientists who ever lived enters the story, and where one of the most instructive mistakes in the history of physics gets made. Isaac Newton tackled the speed of sound theoretically in his Principia Mathematica, published in 1687. Newton tried to calculate the speed of sound from basic properties of air, its density and its pressure. His approach was brilliant in concept. He treated air as an elastic medium, imagined the compression and rarefaction of a sound wave passing through it, and worked out how fast that disturbance should propagate based on the air's resistance to being compressed, which is related to its pressure, and its inertia, which is related to its density. Newton's formula said that the speed of sound should equal the square root of the atmospheric pressure divided by the density of air. Plug in the numbers, and you get a prediction of about 290 meters per second,
which is close to the experimentally measured value, but not close enough. It's about 15% too low. And Newton knew it was too low. He knew the experimental measurements were giving values around 340 to 350 meters per second. And this bothered him. So Newton did something that, in hindsight, was a rare stumble for a man who was almost always right. He fudged the calculation. He added correction factors, adjustments for the spacing of air particles, for the presence of water vapor, for other effects that he argued should increase the theoretical prediction. Some of these corrections were physically reasonable but small. Others were, to put it politely, motivated reasoning. He was trying to make his theory match the experiments, and the adjustments he made were not well justified. The Principia's treatment of the speed of sound is,
by the standards of the rest of that magnificent book, something of a fudge job.
And the error persisted for over a century. Other scientists noticed the discrepancy, scratched their heads, proposed their own corrections, and generally struggled with the same problem. Newton's formula was clearly on the right track. The physics was fundamentally sound, but the predicted value was consistently too low. Something was missing. The resolution came from Pierre-Simon Laplace, the great French mathematician and physicist in the early 1800s. And the insight was subtle, elegant, and deeply satisfying once you see it. Newton had assumed that when a sound wave compresses the air, the compression happens slowly enough that the temperature of the compressed air stays constant. In physics, this is called an isothermal process. But Laplace realized that sound waves compress and expand the air so rapidly, hundreds or thousands of times per second, that there's no time for heat to flow in or out of the compressed region.
The compression happens too fast for the temperature to equalize. When air is compressed quickly without losing heat, it warms up slightly. And warmer air is slightly stiffer, slightly more resistant to further compression. And because stiffness is what determines how fast a wave propagates, the effective stiffness of air during sound propagation is higher than Newton had assumed. Laplace corrected Newton's formula by replacing the isothermal assumption with what's called an adiabatic assumption, one that accounts for the fact that the compression is so fast that no heat escapes. The correction introduced a factor, the ratio of the air's specific heat at constant pressure to its specific heat at constant volume. For air, this ratio is about 1.4. Multiply Newton's too low prediction by the square root of 1.4, about 1.18, and you get a speed of roughly 343 meters per second,
which matches the experimental measurements almost exactly. The discrepancy that had plagued physicists for a century vanished. Newton's physics had been right. His thermodynamics had been wrong. He'd treated air like a slowly squeezed sponge when in reality, at the frequencies of sound, it behaves more like a rapidly compressed spring that heats up as you squeeze it. There's something deeply instructive about this error. Newton, perhaps the greatest physicist in history, made a mistake that persisted for over 100 years. And the mistake wasn't in the mechanics or the mathematics. It was in the thermodynamics, in the assumption about what happens to the temperature of air when a sound wave passes through it. It took Laplace, working at the intersection of mechanics and the newly developing science of heat, to spot the error. And once you see it, it's obvious. Of course, the compression is too fast for heat to escape. Of course, the air warms up. Of course, the effective stiffness is higher. But for a century, nobody saw it. That's how science works sometimes. The answer hides in an assumption so basic that nobody thinks to question it. And Laplace's correction gave us something more than just an accurate number. It gave us a deeper understanding of what determines the speed of sound in any medium. The speed depends on the medium's stiffness and its density. In gases, the stiffness comes from the pressure and the ratio of specific heats. In liquids, it comes from the bulk modulus, the liquid's resistance to compression. In solids, it comes from the elastic modulus, the material's resistance to being deformed. In every case, the same basic relationship holds. Speed equals the square root of stiffness over density. And this is why sound travels so much faster in water than in air, and faster still in steel. Water is about 800 times denser than air, but its bulk modulus is about 15,000 times higher. The stiffness wins enormously, and the speed comes out to about 1,480 meters per second. Steel is even denser, but its elastic modulus is enormous, and the speed reaches about 5,960 meters per second. The speed of sound in air also depends on temperature, and the relationship is simple enough to remember. At 0 degrees Celsius, the speed is about 331 meters per second. For every degree Celsius you increase the temperature, the speed goes up by about 0.6 meters per second. At 20 degrees Celsius, a comfortable room temperature, you get about 343 meters per second. At a hot 35 degrees, it's about 352. Warmer air has more energetic molecules that transmit the push faster. This temperature dependence has real consequences that you've probably noticed without thinking about them.
Sound travels slightly faster in the warm air near the ground than in the cool air higher up. This speed difference bends sound waves upward during the day, which is why distant sounds can seem to fade. But on a calm night, when the air near the ground is cooler than the air above, especially over water, the bending goes the other way, curving sound waves downward, trapping them near the surface. Sounds travel further at night over a calm lake than during the heat of the day. If you've ever heard a conversation clearly from an astonishing distance across still water on a summer evening, temperature gradients in the air were acting like a gentle acoustic lens, bending the sound waves down toward you. And while we're talking about the speed of sound and how it interacts with motion, there's one more phenomenon we should visit, because it connects the physics of sound to something you experience regularly. Have you ever stood at the side of a road and listened to an ambulance approach?
As it comes toward you, the siren sounds higher in pitch. The moment it passes you and starts moving away, the pitch drops noticeably. The siren itself hasn't changed. The ambulance is playing the same frequency the entire time. What's changing is the relationship between the source's motion and the wave it's emitting. This is the Doppler effect, named after Christian Doppler, an Austrian physicist who first described it in 1842. And the explanation is intuitive once you picture it. When the ambulance is moving toward you, each successive compression of the siren's sound wave is emitted from a position slightly closer to you than the one before. The compressions are bunched together, squeezed into a shorter distance. Shorter distance between compressions means a shorter wavelength. Shorter wavelength means a higher frequency. You hear a higher pitch. When the ambulance moves away, the opposite happens. Each compression is emitted from a position slightly farther away, stretching the wavelength, lowering the frequency, dropping the pitch. The effect is proportional to the speed of the source relative to the speed of sound. At everyday speeds, the pitch shift is modest but clearly audible. At very high speeds, approaching the speed of sound itself, the effect becomes extreme. When a source moves at exactly the speed of sound, all the compressions pile up at the same point, creating a massive pressure wave, a shock wave, that we hear as a sonic boom. And when a source moves faster than the speed of sound, it outpaces its own sound waves entirely, creating a continuous shock front that trails behind it in a cone shape. Doppler's original paper, by the way, discussed the effect in the context of light from stars, not sound. He suggested that the color of stars might be affected by their motion toward or away from Earth. And he was right, though the speeds involved are far larger than anything that produces a noticeable effect with sound. The Doppler shift of light is now one of the most important tools in astronomy, used to measure the speed of distant galaxies and, famously, to confirm that the universe is expanding. The same basic physics that makes an ambulance siren change pitch as it passes you also revealed the large-scale structure and motion of the cosmos. That's the kind of connection that keeps showing up throughout the history of sound. An idea that starts small, local, personal, and then turns out to apply at scales that nobody initially imagined. The Doppler effect also has direct practical applications that affect your life. Radar speed guns, the ones police use to catch speeders, work by bouncing a signal off a moving vehicle and measuring the frequency shift of the reflected wave. Medical Doppler ultrasound uses the same principle to measure the speed of blood flowing through your arteries and veins. The probe sends ultrasound into your body. The moving blood cells reflect it back with a slight frequency shift, and the system calculates the flow velocity from that shift. The technology that detects whether a car is speeding and the technology that checks whether blood is flowing normally through your heart are built on the same physics, the same equation, the same observation that Christiaan Doppler made in 1842 about the pitch of a moving source. Now, knowing the speed of sound opens a door that might not seem obvious at first, but it's one of the most important connections in all of acoustics. Because once you know the speed and you know the frequency of a sound, how many vibrations per second the source is making, you can calculate the wavelength, the physical distance between one compression and the next, one crest and the next, as the wave moves through the air. The relationship is beautifully simple. Speed equals frequency times wavelength. Rearrange it, and wavelength equals speed divided by frequency. A concert orchestra tunes to a standard pitch of 440 Hz, meaning the sound source vibrates 440 times per second. The speed of sound is about 343 meters per second. So the wavelength of that tuning note is 343 divided by 440, which works out to about 78 centimeters, roughly the length of your arm. Every time you hear that note, the air pressure between you and the source is rising and falling in a pattern that repeats every 78 centimeters.
There's something wonderfully tangible about that. Sound has a physical size. A low bass note at 50 Hz has a wavelength of nearly 7 meters, the width of a room. The highest frequency a young human can hear, around 20,000 Hz, has a wavelength of about 1.7 centimeters, smaller than a coin. And these physical sizes matter enormously for how sound behaves in the real world. A sound wave can bend around an obstacle if the obstacle is smaller than or comparable to the wavelength. That's why you can hear low-frequency sounds around corners and through doorways much more easily than high-frequency sounds. A bass guitar note, with its 7-meter wavelength, curves around a building effortlessly. A piccolo note, with a wavelength of a few centimeters, casts a sharper acoustic shadow behind an obstacle, much like light does. The wavelength determines how sound interacts with the physical world.
And the connection between frequency, wavelength, and speed gives us one more tool for understanding what we hear. Decibels. We haven't talked about loudness properly yet, and it matters because the way your ear perceives loudness is not straightforward. Your ear doesn't respond to sound intensity on a linear scale. If you double the acoustic energy reaching your eardrum, the sound doesn't seem twice as loud. It seems only slightly louder. To perceive a sound as twice as loud, you need roughly 10 times the acoustic energy. This is why acousticians use decibels, a logarithmic scale that more closely matches how your ear actually perceives changes in volume. An increase of 10 decibels sounds roughly like a doubling of loudness. An increase of 20 decibels sounds like quadrupling. The scale is defined relative to a reference point, the threshold of human hearing, which is defined as 0 decibels. A whisper is about 20 to 30 decibels. Normal conversation is roughly 60. A lawnmower is about 90. The threshold of pain is around 120 to 130 decibels. And a jet engine at close range can reach 140 or more. The range between the quietest sound you can hear and the loudest sound you can tolerate spans about 120 decibels on this logarithmic scale. In terms of actual acoustic power, that's a factor of 1 trillion. 1 trillion. The loudest thing your ear can handle delivers 1 trillion times more energy than the quietest thing it can detect. And your ear handles this entire range smoothly, continuously, without ever saturating or losing resolution, through a combination of mechanical and neural adaptations that engineers still study with admiration. This enormous dynamic range is one of the reasons that audio engineering is so challenging. Capturing and reproducing a range of loudness that spans 12 orders of magnitude in a medium like vinyl or tape or a digital file that has its own noise floor and its own ceiling is a constant balancing act. Every recording format imposes a window of dynamic range, the distance between the quietest signal that rises above the noise floor and the loudest signal that can be stored without distortion. Vinyl gives you roughly 60 to 70 decibels. Magnetic tape, similar. A 16-bit CD gives about 96. A 24-bit digital recording can theoretically achieve 144, which finally approaches the dynamic range of the human ear itself. So now we have the speed, we have the wavelength, we have the frequency, we have the basic mechanics of how a sound wave propagates through a medium. The chain from source to medium is becoming clearer. A string vibrates. The vibration creates alternating zones of compression and rarefaction in the air.
That pattern races outward at 343 meters per second, carrying energy without carrying air. The frequency tells you how many times per second the pattern repeats. The wavelength tells you how far apart the repetitions are. But there's a question lurking in all of this that we haven't addressed yet. A question that seems simple until you really think about it. When you hear a violin and a trumpet playing the same note at the same volume, why do they sound so different? The frequency is the same, the loudness is the same, and yet you can tell them apart instantly, effortlessly, without even trying. Something about those two sounds is fundamentally different. Something beyond pitch and volume.
And figuring out what that something is, finding a way to see inside a sound and understand its hidden structure, required a completely new way of thinking. A mathematical idea so powerful that it would eventually reshape not just acoustics, but virtually every branch of science and engineering. And it came from a place you might not expect. It came from a study of heat. When you pluck a guitar string, the sound you hear is not a single pure tone. It might sound like one note, one pitch, but if you could slow it down, if you could somehow peel the sound apart, layer by layer, you'd find something much richer and more complex hiding inside it. The string isn't just vibrating as a whole, it's also vibrating in halves, in thirds, in quarters, in fifths, and in every other integer division you can imagine, all at the same time. Each of these partial vibrations produces its own frequency, its own tone.
The vibration of the whole string gives you the fundamental, the note you'd name if someone asked you what pitch the guitar was playing. The vibration of the two halves gives you a frequency exactly twice the fundamental, 1 octave higher. The thirds give you 3 times the fundamental, the quarters 4 times, and so on. These higher frequencies are called harmonics or overtones, and every vibrating object produces them. Not just strings, but drums, bells, organ pipes, your vocal cords, everything. When you hear a violin playing a concert A at 440 Hz, you're also hearing, layered on top of that, 880 Hz and 1320 Hz and 1760 Hz and many more, each one an integer multiple of the fundamental, each one slightly fainter than the one before. And here's the key.
The specific blend of harmonics, the relative loudness of each overtone compared to the fundamental, is what gives an instrument its characteristic sound, its timbre. A violin produces a rich, complex mixture of overtones, with certain ones emphasized and others suppressed. And that mixture is different from the one a trumpet produces, which is different again from a flute, which is different from a piano, which is different from a human voice. The fundamental frequency tells your ear the pitch. The harmonics tell your ear what kind of instrument is playing. Think about it like recipes. If the fundamental frequency is the main ingredient, say flour, then the harmonics are all the other ingredients: sugar, salt, butter, eggs, vanilla. The same base ingredient can produce very different results depending on what else you add and in what proportions. Flour plus sugar plus butter plus eggs gives you cake. Flour plus water plus yeast gives you bread. Both are built on flour.
Both would be identified as flour-based if you analyzed their main ingredient. But nobody would confuse a cake with a loaf of bread. The overtones are what make a violin sound like a violin and not like a trumpet, even when both are playing the exact same note. Now, people had an intuitive sense of this for centuries. Musicians knew that different instruments had different tonal qualities, that a flute sounds pure and a trumpet sounds brassy and a violin sounds rich. But understanding why, in physical and mathematical terms, required 2 breakthroughs. The first was experimental, and it came from a German physicist named Hermann von Helmholtz. The second was mathematical, and it came from a French mathematician named Joseph Fourier. And together, they cracked open the inner structure of sound in a way that changed everything. Let's start with Helmholtz, because he's one of those figures whose sheer range of accomplishment is almost hard to believe.
Born in 1821 in Potsdam, Prussia, Helmholtz was a polymath in the deepest sense. He made foundational contributions to thermodynamics, formulating the law of conservation of energy as a young man. He made groundbreaking discoveries in optics, in the physiology of vision, in electrodynamics, in fluid mechanics. He invented the ophthalmoscope, the instrument doctors still use to look inside your eye. If you had to name the top 10 most versatile scientists who ever lived, Helmholtz would be on the list. And in 1863, he published a book called On the Sensations of Tone, which became one of the most important works in the history of acoustics. In it, Helmholtz laid out a comprehensive theory of how we perceive musical sound, and at the center of his approach were the resonators he'd invented. Helmholtz resonators are beautifully simple devices.
Imagine a hollow brass sphere, about the size of a grapefruit, with a small opening on one side and a narrow tube on the opposite side that you'd place near your ear. Each sphere was carefully made to resonate at one specific frequency, and one frequency only. When you held it up in a room full of sound, it would amplify just that one frequency, picking it out from the complex mixture of tones in the environment and making it louder in your ear, while everything else stayed at its natural volume. It was like having a filter for your hearing, a sieve that let one frequency through and blocked the rest. Helmholtz had sets of these resonators, each tuned to a different frequency, and he used them to painstakingly analyze the harmonic content of vowel sounds, musical instruments, tuning forks, organ pipes, singing voices. He'd hold up one resonator and listen for the strength of that particular harmonic. Then he'd switch to the next one.
Frequency by frequency, he built up a complete picture of which overtones were present and how strong each one was. And what he found confirmed the hypothesis about timbre in beautiful detail. Different instruments really do produce different blends of harmonics. A clarinet, for example, produces mostly odd-numbered harmonics. The fundamental, the third harmonic, the fifth, the seventh, with the even-numbered harmonics much weaker. That's why a clarinet has that distinctive, hollow, woody quality. A trumpet, by contrast, produces both odd and even harmonics in a rich, bright mix, which gives it that brassy, assertive character. A flute produces a strong fundamental with relatively weak harmonics, which is why it sounds so pure and clean. Helmholtz could explain, in precise physical terms, why your ear hears these instruments differently. The air pressure wave reaching your eardrum from a clarinet has a different shape than the one from a trumpet, even at the same pitch and volume.
The shape of the wave, the specific pattern of compression and rarefaction, encodes the instrument's harmonic signature. And your ear, as Helmholtz began to suspect, was somehow performing its own analysis of that complex wave, breaking it down into its component frequencies and sending that information to your brain. But Helmholtz's experimental analysis, as powerful as it was, rested on a mathematical foundation that had been laid down decades earlier by someone working in an entirely different field. Joseph Fourier was a French mathematician and physicist born in 1768 in Auxerre, a small town in Burgundy. He had a dramatic life, Fourier. He was orphaned by age 9. He became a prominent supporter of the French Revolution. He accompanied Napoleon on the Egyptian campaign and served as the governor of Lower Egypt for a time. He survived the political upheavals of revolutionary and Napoleonic France, which was no small feat, and eventually settled into a career as a mathematician, working primarily on the problem of how heat flows through solid objects. And it was in the context of heat conduction, not sound, that Fourier proposed the idea that would change acoustics forever. In 1807, he presented a paper to the French Academy of Sciences that made an astonishing claim. Any function, he said, any curve, any shape, no matter how complex, no matter how irregular, can be represented as a sum of simple sine waves. Each sine wave has its own frequency, its own amplitude, its own phase. Add them all together in the right proportions, and you can reconstruct the original shape perfectly. It didn't matter how jagged or smooth, how simple or complicated the original function was. It could always be broken down into sinusoidal components. This was a bold claim, and several prominent mathematicians were skeptical. Joseph Louis Lagrange, one of the leading mathematical minds of the era, objected strongly. He thought the claim was too sweeping, too broad. There were technical mathematical issues about convergence, about whether the sum of sine waves always converges to the original function, especially at points of discontinuity. These issues were eventually resolved by later mathematicians, but the core claim, the fundamental insight, was sound. Any complex wave can be decomposed into simple sine waves. And any combination of simple sine waves can be built up into a complex wave. Think about what this means for sound. When a violin plays a note, the air pressure at your eardrum varies in a complicated way, a complex waveform that encodes the fundamental plus all the harmonics. Fourier's mathematics tells us that this complicated wave can be perfectly decomposed into a collection of simple sinusoidal components. The fundamental frequency, the second harmonic, the third,
and so on, each with its own amplitude. The list of those components and their amplitudes is a complete description of the sound's tonal character. It's the recipe, expressed in mathematical terms, and this process of breaking a complex signal into its frequency components is now called Fourier analysis, and it is, without exaggeration, one of the most important mathematical tools ever developed. It's used in virtually every branch of science and engineering. It's inside your phone right now, in the algorithms that process your voice calls and compress your music files. It's in every piece of medical imaging equipment that uses ultrasound. It's in the software that controls noise-cancelling headphones. It's in the systems that analyze seismic data, process radio signals from space, clean up forensic audio recordings, and tune concert hall acoustics. Fourier analysis is everywhere. And it all started with a claim about heat conduction that several respected mathematicians initially refused to believe. The connection between Fourier's mathematics and Helmholtz's physical investigations was profound. Helmholtz was doing Fourier analysis by hand, using his resonators to pick out one frequency at a time from a complex sound, measuring its strength, and building up the frequency spectrum piece by piece. Fourier's mathematics told him in advance that this decomposition was always possible, that any sound could be broken down this way, that the component frequencies existed whether you measured them or not. The math and the physics reinforced each other perfectly, and then Helmholtz made another observation that connected all of this to biology, to the ear itself.
He proposed that the cochlea, the snail-shaped structure in the inner ear that we'll talk about in detail later tonight, works as a kind of biological Fourier analyzer. Different parts of the cochlea respond to different frequencies, he suggested, performing the decomposition that Fourier described mathematically. High frequencies stimulate one region, low frequencies stimulate another, and the brain receives not the raw complex waveform, but a frequency-by-frequency breakdown, a spectrum, which it then interprets as pitch, timbre, and everything else you hear. Helmholtz wasn't entirely right about the mechanism. The details of how the cochlea actually performs this frequency separation turned out to be more complex and more elegant than he imagined. And it would take until the middle of the 20th century for Georg von Békésy to work out the full picture and win a Nobel Prize for it. But the basic insight that the ear performs a frequency analysis, that it decomposes complex sounds into their sinusoidal components, was exactly right. And it was made possible by the combination of Helmholtz's experimental genius and Fourier's mathematical vision. So let's step back for a moment and see where we are in our chain. We started with vibration, a string moving back and forth because of a restoring force. That vibration produces not just a fundamental frequency, but a whole series of harmonics, a unique blend of overtones that gives each source its distinctive voice. The vibration pushes against the air, creating a complex longitudinal wave that carries the harmonic signature outward at roughly 343 meters per second. And Fourier showed us that this complex wave, no matter how intricate, can be perfectly described as a sum of simple sine waves, each with its own frequency and amplitude. The chain from source to medium is now detailed and rich. We understand vibration, we understand propagation, we understand the inner structure of sound. But there's a question we've been circling around, a phenomenon we've touched on, but haven't fully explored. And it's one of the most powerful and sometimes most dangerous ideas in all of physics. What happens when a vibration meets something that vibrates back? What happens when a sound wave encounters an object that has its own natural frequencies, its own tendency to oscillate. What happens at resonance? And what happens when sound waves bounce off surfaces, overlap with each other, and create patterns that can make a room sound like a cathedral or like a padded box? We need to talk about what happens at the boundaries, because that's where some of the most dramatic and most beautiful physics of sound plays out. You've heard an echo. Everyone has.
You shout toward a cliff face or a large building, and a moment later, your own voice comes back to you, slightly fainter, slightly delayed, but unmistakably yours. The ancient Greeks knew about echoes. They even had a myth to explain them. The nymph Echo, cursed by the goddess Hera to repeat only the last words spoken to her, forever unable to speak first. It's a lovely story, but the physics is lovelier still, because echoes are the simplest example of something that governs the entire world of sound. Reflection. When a sound wave hits a surface, a wall, a cliff face, the flat surface of a lake, part of the wave's energy bounces back. And the rule governing how it bounces is the same one that governs light bouncing off a mirror. The angle of incidence equals the angle of reflection. If the sound arrives perpendicular to the surface, it bounces straight back. If it arrives at a 30-degree angle, it bounces off at 30 degrees on the other side.
Clean, simple, predictable, and identical in principle for sound waves, light waves, water waves, any wave at all. It's a universal feature of wave behavior, not specific to any particular kind of wave. But real surfaces aren't perfect mirrors. They're rough. They're uneven. They absorb some of the sound energy and scatter the rest in various directions. A smooth concrete wall will reflect sound almost cleanly, like a mirror. A heavy velvet curtain will absorb most of the sound that hits it, reflecting very little. A bookshelf full of irregularly shaped books will scatter the sound in many directions at once, diffusing it rather than reflecting or absorbing it. And this interplay between reflection, absorption, and scattering is what determines the acoustic character of every space you've ever been in. Think about a bathroom. Hard tile walls, hard ceramic floor, glass shower door, everything close together. You sing in the shower, and your voice sounds incredible, full, resonant, powerful. That's because the hard, smooth surfaces reflect almost all the sound energy. And because the room is small, the reflections reach your ears almost instantly. So quickly that your brain doesn't perceive them as separate echoes, but as a kind of enrichment, a thickening of the original sound. The reflections pile up on top of each other, reinforcing the voice, filling in the gaps, smoothing out the wobbles. Acousticians call this reverberation, and the bathroom is a highly reverberant space. It flatters any voice. It's the cheapest vocal processor in the world. Now imagine the opposite. You're standing in the middle of a wide open field. No buildings, no trees, no walls, just flat ground and open sky. You clap your hands. The sound radiates outward and just goes. It never comes back. There are no surfaces to reflect it, no boundaries to send it back to your ears.
The clap sounds thin, sharp, dry, immediate. Your voice in that field would sound naked and exposed compared to the bathroom version. Every imperfection audible, nothing softened, nothing enriched. Acousticians call this a free field condition, sound propagating without any reflections at all. Every real room falls somewhere on the spectrum between those two extremes, and the art and science of controlling where on that spectrum a particular space lands, that is the field of architectural acoustics. And the person who arguably invented this field, who turned it from guesswork and intuition into a quantitative science, was a young physics professor at Harvard
named Wallace Clement Sabine. His story begins with a problem that nobody else wanted. In the 1890s, Harvard had just opened a new lecture hall in the Fogg Art Museum, and it was an acoustic disaster. Speakers were unintelligible. Words blurred into each other, swallowed by a wash of echoes and reverberations.
The room sounded muddy, confused, as if the air itself were fighting the speaker. The university president asked Sabine to fix it, apparently because Sabine was junior enough in the department that he couldn't refuse the assignment. What Sabine did next was remarkable for its methodical patience. He started measuring. He'd work late at night, long after the building was empty and quiet, using organ pipes as sound sources and a stopwatch to time how long it took for a sound to decay to inaudibility after the source stopped. Then he started dragging seat cushions from a nearby theatre into the lecture hall, adding them in batches, rows of them, dozens at a time. And after each addition, he'd measure the reverberation time again. Cushion by cushion, methodically, over many nights, he mapped the relationship between the amount of absorptive material in the room and how long sound lingered. What he discovered was a formula. It related the reverberation time of a room to two things: the volume of the room and the total amount of absorption provided by its surfaces and contents. The bigger the room, the longer the reverberation, because the sound has farther to travel between reflections. The more absorptive material you add, the shorter the reverberation, because each reflection strips away more energy. The formula is now called the Sabine equation, and it is the foundation of architectural acoustics. Every concert hall, every recording studio, every lecture theatre, every cinema, every house of worship, the acoustic design of every one of these spaces begins with Sabine's equation. And the unit of sound absorption is named after him. 1 Sabine is the absorption equivalent of 1 square foot of a perfectly absorptive surface, a surface that swallows every bit of sound that hits it and reflects nothing back. Different materials have different absorption coefficients.
A thick carpet might absorb 70 or 80% of the mid-frequency sound energy that hits it. A sheet of glass might absorb only 3 or 4%. A heavy velvet curtain might be 50 to 60%. And these numbers change depending on the frequency, which adds a whole additional layer of complexity. Most soft, porous materials are better at absorbing high frequencies than low frequencies. That's why a room with lots of carpeting and curtains can still sound boomy and muddy. The low-frequency waves, with their long wavelengths, aren't being absorbed effectively. They keep bouncing around, building up, blurring everything. If you're designing a concert hall, you don't just want the right overall reverberation time, you want the right reverberation time across the entire frequency spectrum. Too much high-frequency absorption and the room sounds muffled, dull, lifeless. Too little low-frequency absorption and it sounds boomy and unclear.
The ideal is a balanced decay, where all frequencies fade at roughly the same rate. And achieving that balance requires a careful combination of different materials and structures. Thick, porous absorbers for the high frequencies, tuned panel absorbers and Helmholtz resonators, those same hollow spheres that Helmholtz used for his frequency analysis, now scaled up and built into walls for the low frequencies. Diffusers made of irregular surfaces to scatter mid-range reflections evenly throughout the space. The great concert halls of the world, the ones that musicians and audiences revere, like the Musikverein in Vienna or the Concertgebouw in Amsterdam, were built before Sabine's work, and their wonderful acoustics were partly a matter of luck, partly a matter of inherited architectural traditions, and partly a matter of the right combination of plaster walls, wooden floors, and audience-filled seats, providing a fortuitous balance of reflection and absorption.
After Sabine, architects didn't have to rely on luck anymore. They could predict how a room would sound before a single brick was laid. Let's add one more dimension to the story of boundaries, because sound doesn't just reflect and resonate. It also gets absorbed, and the way different materials absorb different frequencies turns out to have shaped the history of music in ways that most people never think about. Consider a medieval Gothic cathedral. Notre-Dame de Paris, or Chartres, or Cologne. These are enormous stone enclosures with hard, reflective surfaces everywhere. Stone walls, stone floors, stone pillars, glass windows. The reverberation time in a large Gothic cathedral can be 6 to 10 seconds. That means that when a choir stops singing, the sound lingers in the air for nearly 10 seconds before fading to inaudibility. Every note hangs in the space, overlapping with the notes that came before it and the notes that come after.
And this acoustic environment directly shaped the music that was written for it. Gregorian chant, the music of the medieval church, is slow, flowing, with long, sustained notes and gentle, stepwise melodies. Fast passages are avoided. Complex rhythms are avoided. Quick jumps between distant notes are avoided. And the reason is acoustic, not just aesthetic. In a space with a 10-second reverberation time, fast music turns to mush. The notes smear into each other, the rhythms blur, the harmonies pile up into chaos. The only kind of music that sounds clear and beautiful in a Gothic cathedral is exactly the kind of music that medieval monks actually wrote. Slow, sustained, and harmonically simple. The architecture dictated the art. Compare that to a small, dry jazz club with carpeted floors, upholstered seats and acoustic ceiling tiles. The reverberation time might be less than half a second. In that environment, fast rhythms are crisp and clear. Complex harmonies resolve cleanly. A drummer's snare snap sounds tight and immediate. A fast saxophone run is intelligible note by note. The music that flourishes in this kind of space, bebop, with its lightning tempos and dense harmonic language, would sound like a muddy roar in Notre Dame. And Gregorian chant in a jazz club would sound thin, naked and exposed, stripped of all the reverberation that gives it its ethereal beauty. The point is that sound and space have always been entangled. Music is never created in a vacuum, literally or figuratively. The physical environment in which music is performed shapes what kind of music gets created, and the kind of music people want to hear shapes the spaces they build to hear it in. Concert halls, opera houses, recording studios, amphitheaters, churches. These are all acoustic instruments in their own right, as much a part of the sound as the instruments and voices they contain. And this relationship between space and sound has one more twist that's worth mentioning: convolution reverb. In the digital age, audio engineers can capture the acoustic signature of any room in the world and apply it to any recording, as if the recording had been made in that room. The technique works by recording a short, sharp sound, often a balloon pop or a starter pistol, in the space you want to capture. That recording, called an impulse response, contains all the information about how the room reflects, absorbs, and diffuses sound at every frequency. Then, using a mathematical operation called convolution, which is closely related to the Fourier analysis we talked about earlier, you can process any audio signal as though it were being played in that room. The result is astonishingly convincing. You can record a singer's voice in a tiny, dry studio and make it sound as though she's singing in the Sistine Chapel. You can take a guitar track recorded in a bedroom and place it inside the Sydney Opera House. The reverberant character of any space on Earth, or any space that has ever existed, can be preserved as a digital file and applied to any sound at will. What Sabine spent years quantifying with cushions and a stopwatch, we can now reproduce with almost eerie precision using nothing but numbers. But reflection and absorption are only part of the story of what happens when sound meets a boundary. we need to talk about what happens when sound waves overlap, when reflections collide with incoming waves, when two sounds occupy the same space at the same time. Because that's where some of the most beautiful and most powerful phenomena in acoustics emerge. Waves obey a principle called superposition. When two waves meet at the same point, they don't bounce off each other or block each other. They simply add together. At every point in space, the total disturbance is the sum of the individual disturbances from each wave.
If both waves are pushing the air pressure up at that point, you get a bigger push. The waves reinforce each other. That's constructive interference, and it makes a louder sound. But if one wave is pushing up while the other is pulling down, they cancel. The peaks of one wave fill in the troughs of the other, and the result is a smaller disturbance. Or, if the waves are perfectly matched in amplitude, no disturbance at all. Destructive interference. Silence from two sounds combining. Two sounds adding up to no sound. That's a striking idea, and it's not just theoretical. It's the principle behind noise-cancelling headphones, which are one of the most elegant applications of wave physics you'll encounter in everyday life. Tiny microphones on the outside of the headphones pick up ambient noise, the drone of an airplane engine, the rumble of a train car.
A processor analyzes the incoming wave and generates a second wave that's the exact inverse. Same frequency, same amplitude, but with the peaks and troughs flipped. When the original noise and the anti-noise combine in your ear canal, they cancel each other out. Silence, engineered on purpose, computed thousands of times per second. Interference also creates something called standing waves, and this phenomenon is directly connected to the music Pythagoras studied 2,600 years ago, though he had no idea why. When a sound wave bounces back and forth between two parallel surfaces, the incoming and reflected waves overlap. At certain frequencies, specific frequencies determined by the distance between the surfaces, the overlapping waves line up perfectly and create a stable pattern. At some points, called antinodes, the air pressure swings wildly between high and low. At other points, called nodes, the pressure stays almost perfectly constant, barely moving at all. The pattern doesn't travel. It just stands there, oscillating in place. A standing wave. This is exactly what happens on a vibrating string. The string is fixed at both ends, and only certain wavelengths fit neatly between those fixed points. Those are the resonant frequencies, the harmonics we talked about earlier. The fundamental mode has a single antinode in the middle, and nodes at each end. The second harmonic has two antinodes and a node in the middle. The third has three antinodes and two internal nodes, and so on. The string selects its own frequencies based on its length, just as Pythagoras discovered. The standing wave pattern is the physical reason behind his mathematical ratios. And standing waves form in rooms too, not just on strings. If you have a room with two parallel walls, the air between them can support standing waves at frequencies whose wavelengths are related to the distance between the walls. In a small room, this can create noticeable dead spots and hot spots, places where certain frequencies are unnervingly loud and others nearly disappear. Audio engineers and studio designers spend enormous effort breaking up these patterns, using diffusers and absorbers and deliberately non-parallel walls to prevent standing waves from dominating the sound. And now we need to talk about resonance, because resonance is standing waves taken to their most dramatic conclusion. Every object that can vibrate has natural frequencies, frequencies at which it prefers to oscillate, frequencies at which even a tiny input of energy gets amplified because the timing is exactly right. Push a child on a swing at exactly the right moment in each cycle, and the swing goes higher and higher with very little effort. Your small, well-timed pushes add energy to the system faster than friction and air resistance can remove it, and the amplitude builds. That's resonance.
The frequency of your pushes matches the natural frequency of the swing. The same principle applies to everything that vibrates. A wine glass has a natural resonant frequency determined by its shape, its thickness, the material it's made from. If you produce a sound at exactly that frequency, the glass vibrates in sympathy. The sound wave pushes the glass at precisely the right moments in its oscillation cycle, adding energy each time. If the driving force is strong enough and sustained enough, the vibrations can build until the glass shatters. You've probably seen videos of this. A singer hits just the right note, holds it, and the glass explodes. It's not magic, it's resonance. But resonance can also be dangerous on a much larger scale, and the most famous example is the Tacoma Narrows Bridge. It was a suspension bridge in Washington state, opened in July of 1940, and from its very first day, it had a reputation for movement.
The wind would set the roadway undulating, rising and falling in gentle waves, and locals nicknamed it Galloping Gertie. Then, on November 7th, 1940, just 4 months after opening, a steady 40-mile-per-hour wind set the bridge into increasingly violent oscillations. The motion shifted from a gentle vertical bounce to a dramatic twisting, a torsional mode that grew and grew until the entire center span tore itself apart and collapsed into the water below. The popular version of the story says the wind hit the bridge's resonant frequency, and while that's a useful first approximation, the real physics is more subtle. What destroyed Tacoma Narrows was a phenomenon called aeroelastic flutter, a self-exciting feedback loop where the bridge's own motion changed the way the wind flowed around it, which amplified the motion, which further changed the wind flow, and so on, each cycle pumping more energy into the oscillation. The bridge wasn't being pushed at its resonant frequency by an external force. It was generating its own amplification through a feedback mechanism between its structural dynamics and the aerodynamics of the wind. And this idea of feedback-driven oscillation shows up everywhere in the world of sound. The screech you hear when someone holds a microphone too close to a speaker is the same basic phenomenon. The microphone picks up sound from the speaker, sends it through the amplifier, which sends it back out the speaker louder, which the microphone picks up again. Each loop adds energy. The amplitude builds until you get that piercing howl. Audio engineers call it feedback, and managing it is one of the fundamental challenges of live sound reinforcement. At every concert you've ever attended, someone at a mixing board was actively fighting the physics of resonance and feedback, carefully adjusting which frequencies were amplified and which were suppressed to keep the system from tipping into that self-reinforcing loop. So boundaries, surfaces, enclosures, the physical spaces through which sound travels are not passive containers. They shape the sound. They reflect it, absorb it, scatter it, filter it. They create standing waves and resonances and interference patterns. They can make a voice sound rich and full or thin and harsh. They can amplify a vibration until it destroys a bridge. They can cancel a sound so effectively that a roaring airplane cabin becomes a quiet cocoon. We've followed the sound from its source, through the air, through the medium, measured its speed, dissected its inner structure of harmonics, and now watched it interact with the physical world of surfaces and enclosures. The chain is getting long. But there's one more link before we reach the most remarkable one of all. Because up to this point, everything we've talked about is happening out there, in the external world, in the air, in the room. The sound wave is still just a pattern of pressure fluctuations rippling through a physical medium. For that pattern to become something you actually hear, something you experience as music or speech or thunder, or a door closing softly down the hall, it has to get inside your head. It has to enter the body pass through a series of structures so intricate and so improbably well designed that they still humble the best microphones ever built, and ultimately be translated into the language of the nervous system, into electrical impulses that the brain can interpret. And the mechanism that does this, the apparatus your body uses to convert pressure waves in the air into the experience of hearing, is one of the most extraordinary pieces of biological engineering on the planet. The outer ear, the part you can see, the fleshy, curving structure on the side of your head, is essentially a funnel. Its shape is not arbitrary. Those ridges and folds, the ones that make every human ear look slightly different, serve a surprisingly important purpose. They help your brain figure out where a sound is coming from. Sound waves arriving from different directions interact with those ridges differently, producing subtle changes in the frequency balance of the sound before it enters the ear canal. Your brain has learned, over your entire lifetime, to associate those tiny spectral shifts with specific directions. That's partly how you can tell whether a sound is coming from above or below, from in front or behind, even with your eyes closed. The outer ear is not just a collector, it's a direction encoder, sculpting the incoming sound in ways your brain can read.
The ear canal is a short tube, roughly 2.5 centimeters long, and it too has an acoustic function, beyond simply conducting sound inward. Because of its length and diameter, the ear canal acts as a resonant tube, amplifying frequencies in the range of about 2,000 to 5,000 Hertz, roughly the frequency range where human speech consonants live. The sounds that carry the most linguistic information, the ones that help you distinguish between sit and fit and hit and bit, are naturally amplified by the physical dimensions of your own ear canal. Your ear is pre-tuned, by its very shape, to be most sensitive to the frequencies that matter most for understanding speech. That's not a coincidence. It's the result of millions of years of evolutionary pressure, favoring ears that were good at decoding language-relevant sounds.
At the end of the ear canal sits the eardrum, the tympanic membrane, a thin, cone-shaped piece of tissue about the size and thickness of a small fingernail, stretched taut across the opening like the head of a tiny drum. When pressure waves reach the eardrum, they push it inward during compressions and let it spring back during rarefactions, causing it to vibrate in a pattern that mirrors the incoming sound wave. The eardrum is astonishingly sensitive. It responds to pressure variations so small that it moves less than the diameter of a hydrogen atom at the threshold of hearing. Less than a 10/1000th of a meter. At volumes that quiet, the eardrum is moving a distance smaller than a single atom, and your brain still detects it as sound. That level of sensitivity is almost absurd. If your ears were any more sensitive, you'd hear the random thermal motion of air molecules, the constant Brownian buzz of atoms bouncing off your eardrum. You'd hear the noise of the universe itself. Your hearing is tuned to within a hair's breadth of that physical limit. On the other side of the eardrum, in a small air-filled chamber called the middle ear, sit the 3 smallest bones in your body, the malleus, the incus, and the stapes, commonly called the hammer, the anvil, and the stirrup because of their shapes. These 3 tiny bones form a mechanical chain that connects the eardrum to the inner ear, and they perform one of the most elegant bits of mechanical engineering in the human body. Their job is to solve a physics problem. Sound has been traveling through air, a light compressible gas. But the inner ear is filled with fluid, a liquid, and liquids are much harder to set in motion than gases. If the sound wave hit the fluid directly, the mismatch in acoustic properties would cause most of the energy to reflect back, the way sound bounces off a concrete wall. You'd lose about 99.9% of the sound energy, Virtually nothing would get through.
The three ossicles solve this problem through two mechanisms. First, the eardrum is much larger than the footplate of the stapes, the oval window where the stapes connects to the inner ear. Because the same force is concentrated onto a smaller area, the pressure is amplified, roughly by a factor of 17. Second, the lever action of the ossicle chain provides an additional small amplification. Together, these two effects multiply the pressure by a total factor of about 20 to 30, neatly compensating for the energy loss that would otherwise occur at the air-to-fluid boundary. The ossicles are an impedance-matching transformer, a device that adapts the acoustic properties of one medium to another. And they accomplish this with three bones so tiny that all three could fit on your fingertip. Beyond the stapes lies the inner ear, and this is where things become truly remarkable. The cochlea is a fluid-filled tube, coiled into a spiral about the size of a garden pea, with roughly 2 3/4 turns. If you could uncoil it and stretch it out, it would be about 35 millimeters long, roughly the length of a large marble. And along the entire length of this tiny tube runs a structure called the basilar membrane, a thin ribbon of tissue whose properties vary continuously from one end to the other. At the base of the cochlea, near the oval window where the stapes pushes in, the basilar membrane is narrow and stiff. At the apex, the far end of the spiral, it's wider and more flexible. And this gradient of stiffness is the key to everything, because it means that different frequencies of sound cause the basilar membrane to vibrate at different locations along its length. High-frequency sounds, with their rapid vibrations, create the maximum displacement near the base, where the membrane is stiff.
Low-frequency sounds create maximum displacement near the apex, where the membrane is loose and floppy. Mid-range frequencies peak somewhere in between. The cochlea is performing a frequency analysis, spreading the incoming sound out along a physical gradient, sorting it by frequency. This is Fourier analysis realized in living tissue, the mathematical operation that Fourier described on paper in 1807, the decomposition of a complex waveform into its sinusoidal components. Your cochlea performs mechanically, continuously, in real time, without any conscious effort. It does this while you're asleep. It does this while you're talking. It does this while you're listening to a 100-piece orchestra and distinguishing the violins from the cellos, from the oboes, from the timpani, all at the same time, all without the slightest sense of strain. Sitting on top of the basilar membrane are roughly 15,000 hair cells, the sensory receptors of hearing. Each hair cell has a tiny bundle of stereocilia on its top, microscopic filaments thinner than the finest thread, projecting upward into the fluid. When the basilar membrane vibrates at a particular location, the hair cells at that location are displaced. Their stereocilia bend. And here's where the mechanical world of vibrations makes its final handoff to the electrical world of the nervous system. The bending of the stereocilia opens tiny ion channels in the hair cell's surface. Charged particles flow in, changing the electrical potential of the cell. The cell releases a chemical neurotransmitter. The neurotransmitter triggers an electrical impulse in the auditory nerve fiber connected to that cell. And that impulse races along the nerve at roughly 100 meters per second toward the brain. The transformation is complete. What started as a pressure wave in the air, a mechanical phenomenon, has been converted into a pattern of electrical signals, a neural code.
The sound has crossed from the physical world into the biological world. From air to eardrum, to bone, to fluid, to membrane, to hair cell, to nerve, to brain. Each link in the chain is a different kind of energy, a different physical mechanism, but the pattern, the information, survives every transition. The frequency decomposition performed by the cochlea is encoded in which nerve fibers are firing. The amplitude is encoded in how frequently they fire. The timing information that lets you locate sounds in space is preserved with a precision of microseconds. Georg von Békésy, a Hungarian biophysicist working at Harvard, won the Nobel Prize in Physiology or Medicine in 1961 for working out the mechanics of this process, for showing how the travelling wave on the basilar membrane achieves its frequency selectivity. He built physical models of the cochlea, scaled up and filled with fluid, and watched how waves propagated along membranes of varying stiffness. He confirmed that the cochlea behaves as a mechanical frequency analyzer, and his work laid the foundation for everything we now understand about the biophysics of hearing. But the hair cells and the cochlea are only the beginning of the neural story. The auditory nerve carries the signals from the cochlea to the brainstem, where the first stages of processing occur. Your brain compares the signals from your two ears, noting the tiny differences in arrival time and intensity that tell you where a sound is coming from. A sound from your left reaches your left ear a few hundred microseconds before it reaches your right ear, and your brain uses that difference to compute the direction. The processing is fast, unconscious, and remarkably precise. You can detect arrival time differences of as little as 10 microseconds, a 10 millionth of a second. From the brainstem, the signals travel up through a series of processing stations, each one extracting more complex features. By the time the signals reach the auditory cortex, the part of the brain responsible for conscious hearing, the raw pressure wave has been transformed into a rich, multi-dimensional representation that encodes pitch, timbre, loudness, location, and duration. Your brain is building an acoustic picture of the world, a sense of space and distance and presence, constructed entirely from vibrations in the air, and the dynamic range of this entire system is staggering. The quietest sound you can hear involves eardrum movements smaller than the diameter of a hydrogen atom. The loudest sound you can tolerate without pain involves eardrum movements about 1,000,000 times larger. That's a range of intensity spanning 12 orders of magnitude, a factor of 1 trillion from quietest to loudest. No microphone ever built can match that range. No electronic system comes close. Your ear handles it effortlessly, compressing this enormous range into a signal that the brain can process, and it does it all day, every day, from before you were born until the moment you die. And here's the part that stops me every time I think about it. Despite the astonishing sophistication of this biological machinery, despite the elegance of the cochlear frequency analysis and the precision of the binaural localization and the impossible dynamic range, the experience of hearing remains something that science cannot fully explain. We can trace the chain from air to nerve impulse in complete detail. We can describe every physical step. But the final step, the moment when a pattern of neural activity becomes the sensation of a loved one's voice, or the heartbreak of a minor chord, or the instinctive alarm of a sudden crash, that step remains mysterious. How does a pattern of electrochemical signals become an experience? That's not a question about acoustics.
That's a question about consciousness. And nobody has answered it yet. But what we can say, with certainty and with wonder, is that the chain works. It works right now as you listen. The air around you is full of pressure variations. Your eardrums are vibrating, your ossicles are rocking, your cochlear fluid is rippling, your hair cells are bending, your auditory nerves are firing. And somewhere in the darkness of your skull, the experience of hearing is blooming into existence.
assembling a world out of nothing but vibrations. For tens of thousands of years, this chain, from source to ear, was the only chain. Sound happened, traveled through the air, reached a listener, and was gone. Every word spoken, every song sung, every note played, existed only in the moment of its creation, and then vanished forever.
The sound of a Mesopotamian lullaby,
The roar of a Roman crowd, the music at a medieval feast. All of it evaporated into the air the instant it was made, leaving no trace, no record, no way to hear it again. Sound was the most ephemeral experience in all of human life. And then, in the second half of the 19th century, a handful of inventors figured out how to add new links to the chain. Artificial links, mechanical and electrical, and eventually digital, that could capture a sound wave, freeze it, store it, and play it back. And that achievement, the construction of an artificial chain that mirrors the natural one, is one of the most remarkable stories in the history of technology. The first person to capture sound, to make a physical record of a pressure wave in the air, was not Thomas Edison.
That's one of those facts that surprises almost everyone who hears it, because Edison's name is so thoroughly welded to the invention of recorded sound that prying them apart takes a real effort. But the actual first person was a French printer and bookseller named Edouard Léon Scott de Martainville, and his story is one of the most poignant in all of science. Scott was not a physicist. He was a man of books and language, deeply interested in the written word, in shorthand, in the mechanics of transcription. And in the 1850s, he became obsessed with an idea that, once you hear it, seems both brilliant and heartbreaking. He wanted to build a machine that could write down sound. Not play it back, just write it down. He imagined that sound waves, if they could be traced as visible patterns, might constitute a new kind of shorthand. Maybe people could learn to read the squiggles the way they read letters on a page. The air would become its own stenographer. In 1857, 20 years before Edison, Scott patented a device he called the phonautograph. The word means self-writing of sound, and the device was exactly as simple as that name suggests. A barrel-shaped horn collected sound and funneled it to a narrow end, where a thin membrane, a piece of parchment or animal bladder, stretched across the opening. The membrane vibrated in response to the incoming sound, and attached to it was a tiny stylus, a stiff bristle, that scratched a delicate wavy line through a layer of soot on a rotating cylinder. The lamp-black soot was deposited by holding the cylinder over a flame. When someone spoke or sang into the horn, the vibrations of the membrane moved the bristle, and the bristle traced the shape of the sound wave through the soot, leaving a pale, wandering line on a dark background. That was the entire machine. Sound came in, a wiggly line came out.
Scott called these tracings phonautograms, and he made dozens of them over the following years, carefully labeling each one with the date, the type of sound, and whatever other details seemed relevant. He was meticulous about his records, as you might expect from a printer and bookseller. But he never played them back. He never even tried. That wasn't the point for him. The point was the visual record, the written trace. And in this single-mindedness, Scott missed the one leap that would have changed everything. If you can trace the shape of a sound wave, you can, in principle, reverse the process. You can use the trace to drive a membrane, which pushes air, which recreates the sound. The recording becomes a playback device. But that idea simply did not occur to Scott, or if it did, he dismissed it as impractical or beside the point. And here's where the story acquires a tender kind of sadness. For over 150 years, Scott's phonautograms sat in archives in Paris. Fragile sheets of paper with their faint wavy lines scratched through soot, and nobody could hear what was on them. They were silent artifacts of sound, visible traces of voices and music that had been dead for more than a century. Then, in 2008, a group of researchers at the Lawrence Berkeley National Laboratory in California used high-resolution optical scanning and digital signal processing, the direct descendants of Fourier's mathematics, to convert those visual traces back into audio. They essentially photographed the squiggly lines at very high resolution, calculated what frequencies and amplitudes they represented, and synthesized the corresponding sound waves digitally. What they recovered was a recording of someone singing Au clair de la lune, a French folk song, scratched into soot on April 9, 1860. The audio is scratchy, it's ghostly, it wavers and distorts. But it's a human voice from 1860, 17 years before Edison. The oldest known recording of a recognizable human voice made by a man who never heard it played back. Scott died in 1879, the same year Edison was touring the world demonstrating his phonograph to astonished crowds. And by most accounts, Scott was bitter about it. He felt that Edison had received credit for something he had pioneered. And in a sense he was right. But in another sense, he had missed the crucial insight. Because the real breakthrough wasn't recording sound. The real breakthrough was recording it and playing it back. Edison's phonograph, built in 1877, did both. And the mechanism was, in principle, beautifully simple. Instead of scratching a line through soot on a flat surface, Edison's device used a stylus to cut a groove into a sheet of tinfoil wrapped around a rotating cylinder. You spoke into a horn. A diaphragm at the narrow end vibrated. The stylus, connected to the diaphragm, pressed into the foil with varying depth, creating a groove whose profile was an analog of the original sound wave's pressure variations. Then you put the stylus back at the beginning of the groove, turned the cylinder again, and the groove pushed the stylus back and forth, vibrating the diaphragm, pushing air in the same pattern, and the sound came back. The same chain of cause and effect running in reverse, record and playback using a single mechanism. Edison reportedly recited, "Mary had a little lamb," during the first test. When his own voice played back to him from the tinfoil, even he was startled. He later said he was always afraid of things that worked the first time. The demonstration was electrifying. Edison became world famous almost overnight. He was invited to the White House to show the device to President Hayes. People called it the talking machine, and some genuinely accused Edison of ventriloquism, of hiding someone inside the device to fake the effect. The tinfoil phonograph was crude, the recordings degraded after just a few playbacks because the foil was so fragile. But the concept was proven. Sound, that most transient of phenomena, could be captured and brought back. A voice could speak after the speaker had left the room, or left the city, or, eventually, left the world entirely. That conceptual breakthrough was enormous, even if the technology needed decades of refinement. And the refinement came from multiple directions. Alexander Graham Bell, the telephone inventor, along with his cousin Chichester Bell and Charles Sumner Tainter, developed the graphophone in the mid-1880s, replacing tinfoil with wax-coated cardboard cylinders. The wax was more durable, the grooves were cleaner, the recordings lasted longer. Edison, fiercely competitive, responded by switching to solid wax cylinders for his own improved phonograph. But the real disruption in format came from Emil Berliner, a German immigrant living in Washington, D.C. In 1887, Berliner patented the gramophone, and his key innovation was geometric rather than acoustic. Instead of recording a groove spiraling around a cylinder, he recorded it spiraling on a flat disc. Think about the practical consequences. Cylinders are awkward to manufacture,
difficult to store, and essentially impossible to mass-produce quickly. But a flat disk can be pressed from a mold, the same way a page is printed from a plate. You make a master, create a negative, and stamp out as many copies as you want. Berliner's disk format made mass production of recorded music economically viable for the first time. It took about a decade for the sound quality to catch up with cylinders, but by the early 1900s, the disc was winning. And that format, a flat disc with a spiral groove, would dominate the recorded music industry for nearly a century, through shellac 78s, through vinyl LPs, all the way into the 1980s. Now, the early recording process, whether on cylinder or disc, was entirely mechanical. The sound entered a horn, vibrated a diaphragm, and the diaphragm's motion directly cut the groove. There was no electrical amplification anywhere in the chain. The energy to carve the groove came entirely from the sound wave itself, collected and focused by the horn. And this imposed severe limitations. To make a recording loud enough to produce a usable groove, performers had to crowd around the horn and project as forcefully as possible. Orchestras were rearranged based on who could be heard by the horn, not based on musical logic. Singers had to belt at full volume. Quiet instruments like the acoustic guitar were almost impossible to record. The horn was a tyrant, and the music bent to its demands. The revolution that freed music from the horn arrived in the 1920s, in the form of the electrical microphone and the vacuum tube amplifier. A microphone is, in essence, an artificial eardrum. A thin diaphragm vibrates in response to sound waves, and that mechanical vibration is converted into an electrical signal. In a dynamic microphone, a coil of wire attached to the diaphragm moves within the field of a permanent magnet, and the motion generates a tiny electrical current that mirrors the original sound wave. In a condenser microphone, the diaphragm forms one plate of a capacitor, and its vibrations change the capacitance, which produces a varying electrical signal. Either way, the output is an electrical waveform that is an analog of the acoustic waveform that entered the microphone. And once sound became an electrical signal, everything changed.
You could amplify it, boosting a whisper to a shout with vacuum tubes. You could filter it, emphasizing certain frequencies and suppressing others. You could send it down a wire to a recording lathe in another room or another building. You could mix multiple microphone signals together. Performers no longer needed to stand inches from a horn. A singer could stand at a natural distance from a microphone and sing quietly, conversationally, and the electronics would capture every nuance. This is where the entire concept of the crooner comes from. Bing Crosby built his career on a vocal style, smooth, intimate, conversational, that would have been literally impossible to record before electrical microphones. His gentle baritone would have produced grooves so shallow they'd be inaudible on a mechanical phonograph. But with a sensitive condenser microphone and a good amplifier chain, every detail of his voice was captured. The microphone didn't just record the existing art form, it created a new one. The technology shaped the music, which is a pattern that repeats again and again throughout this story. The next great advance in the artificial chain was magnetic tape, developed primarily in Germany in the 1930s and 1940s by engineers at AEG and the chemical company IG Farben. The principle is clean and elegant. A plastic tape coated with iron oxide particles passes over a recording head, which is essentially a tiny electromagnet with a gap. The audio signal, in the form of a varying electrical current, creates a varying magnetic field at the gap, and the magnetic field magnetizes the particles on the tape in a corresponding pattern. On playback, the magnetized tape passes over a similar head, and the varying magnetic field from the tape induces a tiny electrical current in the head's coil. The same mechanism, reversed.
American soldiers discovered this technology in German radio stations at the end of World War II.
And one of the people most responsible for bringing it to America was, improbably, Bing Crosby. Crosby hated doing live radio broadcasts because the format required him to perform the same show twice, once for the East Coast time zone and again for the West Coast. When he heard about magnetic tape, he immediately saw the potential. Record once, broadcast whenever you want. He invested heavily in the Ampex Corporation, which became the dominant American tape recorder manufacturer, and by the late 1940s, magnetic tape had transformed both recording and broadcasting. Tape introduced something that grooves on a disc could never really offer: editing. With a disc, the recording was a single continuous cut. A mistake 3 minutes in meant starting the entire recording over. But tape could be cut with a razor blade and spliced together with adhesive tape. An engineer could take the best sections of multiple performances and assemble them into a single, flawless take.
Sections could be rearranged, mistakes could be excised, individual notes could be removed and replaced. Recording was no longer a document of a single continuous performance. It became a construction, an assembly, a creative act in its own right. And this capability reached its full expression in the 1960s, when a classically trained producer named George Martin and a band from Liverpool named the Beatles started treating the recording studio itself as a musical instrument. Martin and the Beatles worked with 4-track tape machines at Abbey Road Studios in London, and what they did with those 4 tracks was extraordinary. They'd record a vocal at normal speed and play it back at half speed while recording a piano on top. When the combined result played at normal speed, the piano sounded an octave higher and twice as fast, with a strange, harpsichord-like quality unlike any real instrument. That's how they got the keyboard sound on In My Life. They'd feed guitar signals through rotating Leslie speakers designed for organs, creating swirling, Doppler-shifted textures. They'd cut tape into pieces, throw the pieces in the air, and splice them back together in random order. And all of this with 4 tracks. If they needed more layers, they'd bounce, mixing multiple tracks down onto one track of a second machine to free up space, then adding more layers. Each bounce added noise. Each generation of copying degraded the signal. The engineers at Abbey Road were performing feats of signal management, balancing creative ambition against the physical limitations of the medium. The fact that Sgt. Pepper's Lonely Hearts Club Band, released in 1967, sounds as good as it does after roughly 700 hours of studio time and countless tape bounces, is a testament to engineering skill as much as musical genius.
Let's pause for a moment and think about the full signal chain, the complete chain of transduction, because it's one of the most extraordinary sequences of energy conversion in all of engineering. A singer's vocal cords vibrate, pushing air molecules into pressure waves. Those pressure waves hit a microphone diaphragm, which vibrates. In a dynamic microphone, a coil of wire attached to the diaphragm moves within the field of a permanent magnet, generating a tiny electrical current that mirrors the original sound wave. The physics is the motor principle, the same interaction between magnetic fields and electric currents that makes electric motors spin, just applied in a linear back-and-forth motion instead of a rotary one. In a condenser microphone, the diaphragm acts as one plate of a capacitor, and its vibrations change the capacitance, producing a varying voltage that represents the sound. Either way, you now have an electrical signal, and that signal travels through a chain of electronics. Preamplifiers to boost its level, equalizers to shape its frequency balance, compressors to manage its dynamic range, mixing consoles to combine it with other signals. Each of these steps is a link in the chain, and the quality of the final result depends on the quality of every single link. A noisy amplifier introduces hiss. A poor microphone misses certain frequencies. A bad cable adds crackle. Engineers think constantly about signal-to-noise ratio, the relationship between the sound you want and the unwanted noise that creeps in at every stage. The electrical signal eventually drives a recording medium, whether that's a cutting lathe carving a groove in a master disc, a magnetized pattern on tape, or an analog-to-digital converter turning the continuous waveform into a stream of numbers. And on the playback side, the chain reverses.
A needle traces a groove, or a tape head reads a magnetic pattern, or a digital-to-analog converter turns numbers back into a continuous voltage. That voltage is amplified and sent to a loudspeaker, and the loudspeaker itself is a beautiful piece of engineering. The most common type, the moving coil dynamic speaker, works on exactly the same principle as a dynamic microphone, but in reverse. A coil of wire sits inside the field of a permanent magnet, and it's attached to a cone, a diaphragm. When varying electrical current flows through the coil, the interaction between the coil's electromagnetic field and the permanent magnet's field pushes the coil back and forth. The cone moves with it, pushing air, creating pressure waves that mirror the electrical signal. The varying current becomes a varying pressure in the air. The electrical signal becomes sound again. Think about the full chain now. Vocal cords vibrate, creating pressure waves. Those waves hit a microphone diaphragm, creating mechanical vibration. The vibration generates an electrical signal. The signal is amplified, processed, recorded. On playback, the recorded signal is reconverted to electricity. The electricity drives a speaker coil. The coil moves a cone. The cone pushes air. The air enters your ear canal. Your eardrum vibrates. Your ossicles amplify the vibration. Your cochlear fluid ripples. Your hair cells bend. Your auditory nerve fires. Your brain interprets the signal as a voice singing. Every single step is a transduction, energy changing form. Mechanical to acoustic to electrical to magnetic to electrical to mechanical to acoustic to mechanical to hydraulic to electrochemical to neural. And after all those transformations, what comes out still sounds like a human voice. The pattern has survived a dozen complete changes of medium.
The information has been faithfully carried across materials and forces that have nothing in common except the shape of the wave. And then there's Les Paul, who might have appreciated this chain more than anyone because he spent his life pushing its limits in ways nobody else imagined. Les Paul was born Lester William Pulsfuss in 1915 in Waukesha, Wisconsin, and his curiosity about sound technology was boundless and relentless from childhood. As a teenager, he experimented with making his acoustic guitar louder by attaching a phonograph needle to the guitar's body and connecting it to a radio speaker. The crude amplification worked, after a fashion, and it set the direction for his entire career. How do you make the chain longer? How do you add new links? What happens if you do something nobody has done before? In the 1940s, working in his home studio with modified tape machines, Les Paul pioneered a technique he called sound on sound. The idea was deceptively simple but revolutionary in practice. You play a part and record it onto tape. Then you play that tape back through headphones while simultaneously performing a second part, recording both the playback and the new performance onto a second machine. Now you've got two parts on one tape. Rewind. Do it again. 3 parts, again. 4. Each layer adding to the last, building a piece of music that no ensemble could perform live, because it was one person multiplied by technology. Les Paul used this technique to record hit songs with his wife Mary Ford, layering her voice 6, 8, 12 times on top of itself to create rich vocal harmonies that sounded like an entire choir. The records were enormously popular, and audiences had no idea how they were made. The technique predated multi-track recording and was, in many ways, its conceptual ancestor.
When Ampex introduced the first commercial 8-track tape recorder in the late 1950s, partly at Les Paul's urging, the same principle of building recordings layer by layer became the standard approach to music production that it remains today. And it was this layered approach, this idea that a recording could be constructed rather than captured, that George Martin and the Beatles took to its most extreme expression in the mid-1960s, as we discussed earlier. The studio as an instrument. The recording as an object in its own right, separate from any single live performance. Les Paul had planted the seed, and Martin, working with the most creatively restless band in popular music, grew it into something that changed what everyone thought recorded music could be.
Every step in this story, from Edison's tinfoil to Les Paul's tape loops, to the Beatles' 4-track experiments, to today's digital audio workstations with unlimited tracks and zero degradation, represents someone adding a new link to the chain, extending the artificial pathway between source and listener, giving humans more control over what sound becomes after it leaves the air and before it returns to it. And the remarkable thing is that the endpoints of the chain haven't changed at all. It still begins with something vibrating. It still ends with your cochlea decomposing a complex waveform into its frequency components and sending the result to your brain. The technology in the middle has been revolutionized beyond anything Edison or even Les Paul could have imagined. But the ancient chain from source to ear, from air to perception, remains exactly what it always was. But while the Beatles were pushing analog tape to its limits, a different kind of revolution was quietly developing. One that would eventually make concepts like tape hiss and generation loss obsolete entirely. And it started with a question that engineers at Bell Labs had been thinking about since the late 1920s. What if, instead of recording sound as a continuous physical trace, you could record it as numbers? Harry Nyquist, a Swedish-American engineer at Bell Labs, published a paper in 1928 about the capacity of telegraph systems, about how much information you could send through a communication channel. And buried in his analysis was a principle that would become one of the most important theorems in all of signal processing. If you want to accurately capture a signal that contains frequencies up to some maximum value, you need to sample that signal, measure its value, at least twice per cycle of that maximum frequency. If you're trying to capture audio up to 20,000 Hertz, roughly the upper limit of human hearing, you need at least 40,000 samples every second. This became known as the Nyquist theorem, and it was later refined and rigorously proven by Claude Shannon, also at Bell Labs, in his landmark 1949 paper on information theory. Shannon showed that if you sample at or above the Nyquist rate, you can perfectly reconstruct the original continuous signal from those discrete samples. Not approximately, perfectly. Every detail of the original wave is captured in those numbers, as long as you've sampled fast enough. A continuous, flowing, infinitely detailed sound wave can be represented exactly, with zero loss of information, by a list of numbers. Think about what that means. It means that the analog world and the digital world are not fundamentally different in what they can express. They're different languages for saying the same thing. A wave and a list of numbers can contain identical information. And once your sound is a list of numbers, entirely new possibilities open up. You can copy it without any degradation. Remember the bounce problem with tape? Every copy added noise. Every generation was slightly worse than the last. But a number is a number. You can copy the number 42 a million times and it's still 42. There is no generation loss. You can also manipulate those numbers with mathematics, filtering, transforming, combining them with a precision that the analog world simply cannot match. The technology to do all this at useful speeds took decades to develop. In the 1950s and 60s, digital audio required rooms full of equipment and was absurdly expensive. But transistors replaced vacuum tubes, integrated circuits replaced individual transistors, and the cost and size dropped relentlessly. By the early 1970s, Nippon Columbia, the Japanese company known as Denon, was making some of the first commercial digital recordings using custom-built converters. The audio quality stunned engineers who heard it. No tape hiss, no wow and flutter, just music, captured as numbers, played back with a clarity that seemed almost unnatural. The consumer format that brought digital audio to the masses was the compact disc, developed jointly by Philips and Sony and launched in 1982. The CD samples audio at 44,100 times per second, comfortably above the Nyquist rate for 20,000 Hz audio, and stores each sample as a 16-bit number, meaning each measurement can have any of about 65,500 possible values. That gives a theoretical dynamic range of about 96 decibels, a massive improvement over the 60 or 70 decibels achievable on a good vinyl record or tape. The disc itself is a polycarbonate plastic circle about 12 centimeters across, with a thin layer of aluminium inside. A spiral track of tiny pits and flat areas, the pits barely half a micrometer wide, encodes the digital data. A laser beam reads the track as the disc spins, and a photodetector converts the pattern of reflected light into ones and zeros. Those ones and zeros are then run through a digital to analog converter, turned back into an electrical waveform, amplified, and sent to a speaker. The chain is laser to photodetector to digital signal processor to digital to analog converter to amplifier to speaker to air to ear. And built into the CD is a sophisticated error correction system that allows the disc to play perfectly even with small scratches or dust. The data is interleaved and redundant, so that lost or corrupted bits can be reconstructed mathematically.
It's like writing every sentence of a book twice in two different places. If coffee spills on one page, you recover the text from the other copy. The engineering is elegant, and it made the format remarkably robust. The CD transformed the music industry within a decade, essentially replacing vinyl as the mainstream format. But the CD was also, without anyone fully realizing it at the time, the beginning of the end of physical media altogether. Because once music was digital, once it was just numbers, it could be stored on any medium that stores numbers. A hard drive, a flash memory chip, a signal transmitted over a network. It didn't need a special disk, it didn't need a laser, it just needed a processor to decode it and a speaker to turn it back into air. And that realization led to the world we live in now, where most of the music people listen to has never existed as a physical object.
It's data, flowing through fiber optic cables and wireless signals, decoded by the processors in your phone, converted back to analog by a chip smaller than your smallest fingernail, pushed out through a speaker or a pair of earbuds, and turned back into pressure waves that enter your ear and start the ancient biological chain all over again. The artificial chain has grown enormously long and complex since Edison's tinfoil phonograph. Microphones, amplifiers, analog to digital converters, compression algorithms based on psychoacoustic models of your hearing. error-correcting codes, network protocols, digital to analog converters, amplifiers again, speakers. Each link is a feat of engineering. Each link depends on the same fundamental physics of sound waves, vibration, and wave propagation that we've been talking about all night. And yet, despite the extraordinary complexity of the technology, the experience of hearing remains fundamentally the same as it has always been. When you listen to music through streaming earbuds, your cochlea doesn't care whether the pressure waves came from a live orchestra or from a digital to analog converter fed by a stream of data packets. The biological chain is indifferent to the source. It just does what it has always done: convert pressure waves into neural signals, decompose complex waveforms into their frequency components, transmit the result to the brain for interpretation. The technology at the front end of the chain has been revolutionized beyond recognition. The biology at the back end hasn't changed in 100,000 years. And somehow, across all those links, across all those transformations of energy, the music still arrives. So, here you are, lying in the dark, wherever you are, whatever time it is, whatever kind of day you've had. And the chain is working. It's been working this whole time, of course, through every word of this story, through every fact and every name and every date.
The air around you has been carrying my voice to your ears as a pattern of compressions and rarefactions. Tiny fluctuations in pressure, rippling outward at 343 meters per second. Your eardrums have been vibrating, your ossicles rocking, your cochlear fluid rippling, your hair cells bending, your auditory nerves firing. And somewhere, deep in the quiet machinery of your brain, those signals have been assembled into language, into meaning, into the feeling of someone talking to you about the history of sound late at night. Every link in the chain has performed its function. The vibration of the source, Pythagoras' ancient mystery. The wave in the medium, Aristotle's intuition, confirmed by von Guericke's bell in a jar. The speed of transmission, measured by Mersenne from a cannon's flash, refined by Durham in a church tower, explained by Newton and corrected by Laplace.
The harmonic structure, dissected by Helmholtz with his brass spheres, made mathematically rigorous by Fourier's extraordinary claim that any waveform is a sum of simple sine waves. The behavior at boundaries, the reflections and absorptions that Sabine quantified with seat cushions and a stopwatch in an empty lecture hall. The biological transduction, that improbable chain of membrane and bone and fluid and hair cell that your body uses to turn pressure into perception. And the artificial chain, the one that humans built, link by painstaking link, from Scott's soot-covered cylinder to Edison's tinfoil, to Berliner's flat disc, to the electrical microphone, to magnetic tape, to digital sampling, to the stream of data that brought my voice to your ears tonight. We followed the sound on its entire journey, from the moment something vibrates to the moment your brain turns that vibration into the experience of hearing.
And at every link, someone had to figure out what was happening, often by getting it wrong first. Often by looking at a problem from an angle that nobody else had considered. Often by making a connection between two things that seemed unrelated until the right person noticed the thread between them. Pythagoras connecting hammers to mathematics. Mersenne connecting Friar's patience to frequency. Huygens connecting pebbles in a pond to the way waves propagate. Fourier connecting heat conduction to the decomposition of complex waveforms. Helmholtz connecting brass resonators to the physiology of perception. Sabine connecting seat cushions to the architecture of sound. Edison connecting a vibrating membrane to a piece of tinfoil and hearing his own voice played back to him for the first time.
Nyquist and Shannon connecting the continuous world of waves to the discrete world of numbers. And every single one of them would have appreciated the same thing, that the chain holds.
That the pattern survives. That a vibration in the air can pass through a dozen transformations of energy, from mechanical to acoustic to electrical to digital to electrical to acoustic to mechanical to hydraulic to electrochemical. And at the end of all of it, a human being hears music, or speech, or the comforting sound of another person's voice in the dark. The air around you is full of vibrations right now. Some are too faint to hear. Some are at frequencies beyond the range of your perception. All of them are real. All of them follow the same laws of physics that have governed the universe since long before there was anyone around to listen. And your ears, those extraordinary, improbable, beautiful instruments, are translating those vibrations into experience, into meaning, into the feeling of being here, in this moment, in this room, alive and listening. You've been listening for a while now, and maybe some of what we talked about will stay with you. The next time you hear an echo, you might think about Sabine and his seat cushions. The next time you put on noise-cancelling headphones, you might think about destructive interference, two waves adding up to silence. The next time you hear a violin and a trumpet playing the same note, and your ear tells them apart instantly, you might think about Helmholtz and Fourier, and the harmonic recipe that gives each instrument its voice. Or you might not think about any of it. You might just listen. The way people have always listened. The way they listened long before any of these things had names. Sound was here before we were. Wind through trees, water over rocks, thunder rolling across a plain. The physics of pressure waves propagating through a medium didn't wait for humans to discover them. They were operating when the first creatures developed the ability to sense vibrations, hundreds of millions of years ago, long before anything like an ear existed, and they'll continue operating long after we're gone. The universe will keep vibrating. Waves will keep propagating. The chain will keep running, with or without anyone at the listening end. But right now, tonight, you're at the listening end, and that's enough. Let the ideas settle. Let them drift. They'll be there in the morning if you want them. Right now, the only link in the chain that matters is the quiet one. The one between the sound of my voice and whatever gentle corner of your mind is still awake. Your ears will keep working. They always do. They'll keep their quiet watch over the acoustic world around you, keeping you connected, keeping you oriented, keeping you safely here, even as you let go and drift. The chain doesn't need your attention. It runs on its own. It has been running all your life. Let it carry you now, gently, the way a wave carries everything it touches. Not by force, but by the soft, patient, repeating rhythm that the universe seems to prefer above all others. Just rest. The sound will still be there in the morning, doing what it has always done, waiting quietly, carrying the world to you, one gentle wave at a time. And that ancient chain has one quality that the artificial chain, for all its brilliance, has never managed to replicate completely: The emotional directness of sound. A minor chord can make you melancholy. A sudden loud crash can make your heart race. A familiar voice can make you feel safe. These responses are not intellectual. They are not learned, at least not entirely. They are wired into the deepest, oldest parts of your brain, into regions that evolved long before language, long before music, long before anything we'd recognize as culture. Sound was the first warning system. The crack of a branch in the dark. The growl of a predator.
The cry of an infant. Long before our ancestors could see danger, they could hear it. Long before they could speak, they could recognize the emotional tone of a vocalization. Threat, comfort, distress, reassurance. The auditory system is faster than the visual system in many ways. A sudden sound triggers a startle reflex in about 50 milliseconds, far faster than conscious thought. Your body responds to sound before you know what you've heard. The chain from ear to amygdala, the brain's emotional processing center, is fast, direct, and ancient. That's why music moves you, not because of what it means in any linguistic sense, but because of what it does to the chain, to the biological sequence of transductions and neural activations that are as old as hearing itself. A perfectly timed rhythmic pattern triggers motor responses, the urge to tap your foot, to nod your head, because rhythm was, for millions of years, the sound of movement, of approaching danger, of group activity. A dissonant interval triggers a mild stress response, because dissonance signals a kind of acoustic unpredictability, and unpredictability, in evolutionary terms, was worth paying attention to. A resolved chord, a tension releasing into consonance, triggers a small reward response, because the resolution of uncertainty is something your brain has been designed by evolution to find satisfying. None of this requires you to know music theory. None of it requires you to have studied acoustics. The chain handles it all before consciousness gets involved. The hair cells bend, the nerves fire, the brainstem processes, the amygdala responds, and you feel something. You feel it before you understand it, and sometimes you feel it without ever understanding it at all.
The emotional experience of sound is the oldest part of the chain, and in many ways the most miraculous. We can describe every physical step from vibration to nerve impulse. But the step from nerve impulse to feeling, from electrochemical signal to the ache of a cello or the joy of a familiar melody, that step remains as mysterious as it was when Pythagoras first stopped to listen at the blacksmith shop 26 centuries ago.